We're going to make the slides available after the end of the event once we've gathered them all together, so don't worry about that. We will take care of that, and we have your registrations details. We'll be able to send you links to that. And I'd like to extend a welcome also to some participants who are joining online. We're going to stream this event, so you need to be aware of that when you're asking questions. And please give your affiliation when you ask questions. And the recording of the event will be available afterwards. And again, we'll include that in the post-event email. I said I'd say a little bit about IDLES. It's a curious acronym, isn't it? I came up with that acronym as a holding acronym while we were writing the proposal, thinking we would come up with something with slightly better connotations as we went through the process. And we're nearing the end of the project, we haven't done that. Anyway, underneath that acronym is the fact that it's about integrated development of low-carbon energy systems. And that really says a lot about what we set out to do. We set out to look at a whole energy system viewpoint. How you define the boundaries of a whole energy system could be up for debate, but we certainly are looking across various vectors, so across gas, electricity, heating and transport use of energies. And we're looking from top to bottom. We're looking at demand, how it evolves, how you model it, up to national and indeed international system planning. And we're trying to develop tools that aid the long-term understanding of how energy systems evolve. We had 5 years of funding. That basically is near the end. We'll have a few activities that will close in the early part of 2024, but essentially we're at the close of the programme now. So what we're doing in this last of our annual dissemination events is really showing you where we've got to, pretty much the end of the programme. And I want to make a note and pay thanks to the Energy Futures Lab. That's one of the 7 Global Challenge Institutes at Imperial. It's been the host of this programme. Energy Futures Lab helped us work across the various departments and faculties of the college, draw together a wide range of expertise and help us manage that process. I'm grateful to all of the partners who've helped us in this. So UK Research and Innovation, and particularly Engineering and Physical Sciences Research Council, which were the main funder of this work. Not the only funder. We have a number of partner organisations, some of whom helped us with direct funding, particularly Hitachi Energy, EDF, National Grid, Electricity System Operator, and Equinor, and others here made significant in-kind contributions with data and with advice. And I would like to pay thanks to many people who gave up quite a lot of time over the course of this on our management committee and our steering committee, helping us to guide the progress of the research with their insights and their very probing questions about what it is we were setting out to do. We ran the programme in 3 phases. The first phase was developing a set of modelling tools and gathering data. We then applied those modelling techniques to some case studies, and in the third phase, we've been looking at how do you use those modelling tools and that data to answer policy-relevant questions, and you'll see some of the outcomes of that as the day progresses. You have the programme available either by following the QR code or you've got a copy of it in front of you, but let me just quickly review. When I've finished speaking in a couple of minutes' time, we're going to hear from Aruna and from Jacek about, sorry, that went forward without me expecting it to, about some of the demand-side modelling. We'll hear about our work on the role that negative emissions technology should play in a long-term energy plan. We will then have a session where we've got some quick introductions to the posters. We have some of the work that couldn't get squeezed into this programme is going to be displayed on posters, which will be available over lunchtime. And just to give you a little flavour of that, we've got some introductions. Then very pleased to have Carolina Torta here just before lunch to give a keynote address from the perspective of National Grid, ESO. In the afternoon, we're going to launch one of our briefing papers, so the full text of that briefing paper will be available at the end of the day as a PDF, and Malta and colleagues are going to introduce that, and we'll have a panel discussion of that. We've then got some further talks about research outcomes, so I'm going to skip over that a little bit. And then we're going to end the day with some quick-fire introductions to some of the models and other data sources that we've made publicly available and will be curated by us for a number of years to come. So with all of that said, last and importantly, a further networking opportunity at the end of the day. We've got some drinks and canapes in the senior common room, which is just along the main walkway. I'll give you advice on that shortly. And that will close out the evening. So my great pleasure now to welcome my colleague Mirabel Mules, who is going to chair the next stage of this conference and introduce the first set of speakers. Thank you.
Hi everyone, so I'm Mirabel. I'm an associate professor in the business school here at Imperial, and I'm part of IDLES. And it's my pleasure to chair this morning session, and we're going to start with a talk by Aruna Sivakumar, who's a reader in consumer demand modeling and urban systems, and by Dr. Jacek Pawlak, who's research fellow in the Urban Systems Laboratory and the Center for Transport Studies at Imperial, and they're both part of our Department for Civil and Environmental Engineering. They are going to talk about transition towards low-carbon residential heating and tell us about the progress on the large-scale household survey that has been taking place within IDLES. So thank you. So, and you can keep your questions for the end of the presentation.
Thank you. Good morning, everyone. So the two of us will be doing this as a bit of a tag team. I will start by introducing what the work is about, and then Jacek will tell you more about the survey. Now, this presentation is probably going to be different from most of what you're going to hear the rest of today in the sense that, A, it's very demand and consumer focused, and that's been the focus of all of my research and my research group's work in IDLES over the last few years. And so we're going to look specifically at the consumer perspective in terms of the transition to low-carbon residential heating. Specifically, let me give you a bit of an overview of what this presentation is about today. I will talk about the background for what we're presenting today, but also the research behind this, and a summary of the overall approach. There's a lot of different people who contributed to this because, as I said, our expertise is in consumer perspective demand modeling, but there's a lot of technological expertise as well. So this was in close collaboration with a number of others. So I'll talk about that. And then Jacek will present to you the data collection that we're doing, 2 waves of a survey, and how it links to our demand modeling framework. And then finally, this is where I said this is the other reason it's going to be a different presentation from the others. Rather than just questions, what I'm really anticipating is a very active contribution to this survey instrument itself. If you can give us inputs and feedback, wave 1 of the survey is due to go anytime now. It's been ethics approved. And so your inputs could make that bit of a difference to the results actually being valuable over the next few years or more to come in terms of the consumer perspective. So really encourage you to provide inputs and feedback. So if you could think about what we're presenting now as fodder for critical comments, that would be really appreciated. With that, I don't have to talk to this group about the pressure to decarbonize and that there are multiple strategies, one of which is the heating and cooling sector. There's a lot of data about that, about the heating and cooling sectors contributing to almost half of the total energy consumption, etc. And the fact that there are a number of low-carbon alternatives in the market and still evolving in the market in terms of heat pumps and hydrogen boilers and others even. But despite all of those advancements, and despite a lot of, well, some might argue or question the sincerity of the efforts, but despite the efforts on the government, from the government of subsidies and so on, the uptake of the low-carbon heating technologies doesn't match up to the stated objectives or longer-term objectives. And there's a number of reasons for this, the most obvious of which is always cost, and there's substantial capital cost of the new heating technologies. The other, almost equally obvious whenever there's a new technology, is awareness, consumer awareness, their understanding of the reliability, the real value or benefits to themselves as well as the environment. All of these are murky, to say the least. And in the midst of this, there's lots of studies that look at consumer attitudes and perceptions, but being able to quantitatively analyze willingness of consumers to financially invest in that transition and to understand how these decisions affect different segments of the population still remains a bit of a gap, and a big reason for that is data. While we've had access to some large existing data sets of smart meters, etc., that doesn't tell us how these consumers will behave or the choices that they will make in an uncertain future with a new technology or new services for that matter. And that's where that was the motivation for designing a new data collection effort, and that's exactly what we've done now. This is a self-contained piece of work that will be completed in about 3 months or so, and then will feed into a larger piece of work that's led by Professor Christos Markides about the role of future heating technologies. So this data, in this presentation, I'm going to focus obviously on this data collection effort. It's a 2-wave online survey. It's aimed at UK residents, and we're targeting a sample size of about 1,000 respondents. And it will happen in 2 waves, because in wave 1, we're focusing on the status quo, and Jacek will tell you a lot more about that. And wave 1, in fact, the whole design was based on a number of inputs from policy documents, literature, current surveys, speaking to a number of experts, both academic and industrial. And then we generated the 2 waves. The second wave, unlike wave 1, is about looking towards the future. What are these future technologies? And given hypothetical scenarios called stated choice experiments, what choices will people make? And these stated choice experiments will be characterized by the costs of the technologies, emissions impacts, nuisance factor, convenience, a number of other things. And then the outputs, of course, will be not only analysis of this data to produce metrics such as willingness to pay, but we can and we do intend to embed it into our agent-based demand model system, which Jacek will again tell you about, and it will feed into the larger project about the future of heating technologies. I'm actually going to skip over this, and Jacek, maybe you can come to the quotas when I finish, just briefly talking about the acknowledgements. So as I said, this was one of the most multidisciplinary small pieces of work that I've done that's been very multidisciplinary. So we worked very closely with colleagues in chemical engineering, as well as had a lot of feedback from colleagues at EDF, for which we're really thankful, because we had a very interesting discussion focused on the survey. So with that, I'll hand over to Jacek, who'll talk about the sampling strategy as well as the survey.
Okay, thank you, Aruna. Good morning, everyone, once again. So very quickly to take you through, what's been pretty much taking a lot of my time over the past few months in terms of trying to design a survey that will sort of shed some light in terms of how willing people would be to sort of transition from the current way that they heat their homes towards more low carbon options. And one of the first questions that came up was, who do we ask? If there is someone living in a property, should we ask the person living in the property? Should we ask the owner of the property? Sometimes it's the same person or the same household, sometimes it's not. Then there was a question about whether we should ask, any property types with any type of existing heating. And then the question came up, obviously, well, maybe we should focus a bit more on, for instance, gas boiler versus, some of the other options and so on. And that effectively led us to what we needed to do in terms of quotas. So effectively identify segments and thinking about how many people from each segment we would like to survey and with what types of questions. So what we've gone through was the process of identifying some of the sort of qualifiers or like filters that allow us to sort of segment people into various groups. And these were specifically, whether the person or the household living in the property owns that property, whether they have another property that they might be renting out, whether they've got a gas boiler, whether they recently went through the process of replacement the heating system, as well as whether they are member of what we call biased occupations. So, whether they, for instance, work for the government, for the utilities companies, because we believe that these type of occupations might have some sort of inside knowledge that might not sort of give us a good sort of a good understanding of what the sort of general population is like. And once we went through that process and we sort of went through all the different combinations, we identified which questions would be more suitable to ask people or not, depending on which group they belong to. Our primary focus is on owners of properties, because they're effectively the decision makers in terms of replacement of the heating system, in terms of incurring the cost, etc., etc. But we also have some questions that we ask to all the other groups. Altogether, we are aiming for a sample of about 1,100 respondents in sort of both waves, and we will see how it goes. Though we know that it might be sort of something that that might be tricky to achieve, but at the same time we did similar surveys in the past and it went well. With that, I'll jump to the content of the survey that, as Aruna mentioned, literally a few days ago went through ethical approval, which is a long story in terms of how much ethical approval one needs to go through to ask a person whether they would like to replace their gas boiler, but that's a separate story. But this is now pretty much approved, and in the wave one, so in the first survey that we are about to launch, though we've also noticed that, with the recent declarations by the government, we might need to revise some of the questions in terms of, whether people are aware of the commitments to net zero, etc. Having said that, in wave one, we want to understand what is the current status of the heating system in the property that people live in, or they might be sort of renting out. And it's stuff like, the type of property, whether, it's a detached house or whether it's an apartment, what's the size of the property, what's the type of insulation, what are the appliances, etc., etc., etc. I was quite tempted to actually include the entire list of questions, but, it will probably take me to the evening to sort of present all of them. So in terms of groups, the next obvious set of questions is about the existing heating system. So whether, what's the source of heat, when was it replaced, how is it used in terms of, what are the sort of temperature settings, etc. Then the heating costs and tariffs based on a recent bill. So we asked the respondent actually to start the survey being prepared with their most recent heating bill, whether it's a gas or electricity bill or sort of heating bill. Then about the households themselves. How large is the household, what's the composition, what's the lifestyle, are they employed, do they work from home, when do they shower, for instance. These are all the questions that we have in the survey, and we would like to just build that sort of profile in terms of how people use the heating systems. And then it's also about the opinions and attitudes. Do people believe in the climate change? What's the attitude towards the commitment to net zero? Attitudes towards new technologies, do people trust new technologies or not in general, and in terms of heating? How much do they know about these technologies, such as heat pumps, hydrogen boilers, and so on? And then there are some of the questions that colleagues from other groups told us about is, can we ask people about what is the sort of acceptable payback period that people would like to see when they sort of replace their heating system? So it's like a very direct question. We don't know whether it's going to work, I'll be honest with you. But we are trying. This is part of the research that, let's see what happens when you ask a person, what's going to be the sort of payback period which you would expect this sort of return to happen. Just to give you an example of how we want people to report on the existing heating system. So there are three ways in which people can tell us about their heating system specifically. So since we focus primarily on gas boilers, we will ask people to either give us the name of the manufacturer and the sort of boiler type and any sort of attributes that they are able to identify, or take a picture of the nameplate or data plate, if you want to call it, and upload it, or type the serial number and any other information that might be useful. Similarly, we provide an example of a utility bill and just indicate to people, okay, that's the piece of information that we would like to give us, if possible. Obviously, people can refuse to respond. That's why we are aiming for a reasonably large sample, because our previous experience is that with a reasonably large sample, you get enough information to actually be able to model these things. Now, why do we need all of that information? Well, the reason we need that type of information is that what we want to do in wave 2, which is pretty much still work in progress, is that we want to create hypothetical scenarios where a person is facing the choice of replacing the existing heating system with some other alternatives, such as hydrogen boiler and air source heat pump. So these were the two alternatives that we decided to focus on. But we also want to provide them with realistic costs of how much it would cost in terms of replacing, running it, in terms of the emissions and so on. And to do that in a realistic fashion, you need models that take the sort of existing heating system, existing usage profiles, etc., and produce the sort of expected costs, etc. And this is where some of the colleagues from across IDLES will sort of bring their sort of technical expertise and help us sort of compute these costs. So effectively, people will be faced with these sort of scenarios, and they'll say, well, given the costs, the number of maintenance visits, the sort of support that I may be getting, that would be the option that I want. And we do it a number of times with the same individuals by slightly changing the attributes so that we can actually measure the sensitivity, how sensitive people are when we change the costs a bit. And through appropriate subsequent analysis and the sort of using the so-called discrete choice analysis, we are then able to elicit these sensitivities, convert them into willingness to pay, for instance, for certain source of heat, or how much people will be willing to sacrifice in terms of for instance, the emissions, or in terms of the number of maintenance visits if you change the cost and so on. So how people trade off between these things. This is effectively what we are after. And this slide is literally just demonstrating more visually what I've just said, which is in wave 1, we want to understand the status quo. We want to understand what is the current system, how it is used, and so on. That is then fed through the IDLES knowledge, IDLES technical knowledge, to produce things such as, what is the available equipment that people can potentially acquire, and therefore what would be the costs, what would be the capital cost, what would be the running cost, what would be the associated emissions. And that then allow us to produce those realistic scenarios in wave 2. So in terms of the expected timelines, that's always probably one of the trickiest ones to kind of commit to. But initially we were hoping that by now we will be presenting some results. Unfortunately, it went as it went, especially with the sort of amount of ethical approvals that we had to go through. So we are now on the verge of starting the data collection, which we hope to complete at some point in October. And at that point, we will be also working with colleagues to produce the sort of wave 2 questions, or the attributes, the sort of values. And therefore, at some point in November, we'll be starting with the wave 2 questions, so asking people about the willingness to choose between the different sort of low carbon heating options in this sort of scenario context. Once this is done, we give ourselves a few months to crunch the data, to process it into state that will be edible for researchers. And therefore, we expect that at some point in January, we'll have wave 1 questions ready for analysis, for taking and using it as inputs to other pieces of research. And wave 2 will be around March time as an output.
That's 2024.
Sorry, 2024, obviously. Yeah, we've not cracked yet this sort of travel time, I think, but we're close to that, I guess. Obviously, that is all then linked back to all the things that we've done so far within IDLES. So you might recall from previous year's conference that we're also the people responsible for this sort of demand modeling framework that was stitched together within the context of earlier phases of IDLES. So what we are planning now to do is that, because we will have a good understanding of how people will behave, or how people currently behave in terms of using heating, and how people might behave in the future in terms of acquiring new heating systems, we want to effectively link that information to the population synthesizer. So we will not only say that this is the household and so on, but given the properties, the attributes of the household, we'll say, okay, that household is more likely to, for instance, have a gas boiler as their heating system. And then that then allows us to also compute almost like the profile of their heating heating demand over the course of a day, because that's the kind of time horizon that we tended to focus in this context. So these are the sort of two things that we will start with, and obviously I'm sure that ideas will sort of emerge as we go through that process. But that's the vision, how this is all linked back to the outputs from IDLES so far. And with that, I just wanted to sort of close this current presentation with an invitation to provide inputs and feedback. So obviously I don't have the full list of questions, but if you're interested in learning more about what are specifically the questions that we have in the survey, please feel free to talk to us or email us. We'll have email address at the end with ideas for what you think would be useful to have in such a survey. And then the thing that we are very interested in is, you've seen the way that we want to present these sort of options. It's going to be a bit sort of nicer in terms of the graphics, but you probably get the idea. What should be the sort of attributes? It's the costs, it's the emissions, nuisance. What else? Is it the number of maintenance visits, types of support that people could receive? Because these are the things that we have a quite unique chance to test in terms of what people would prefer to see. And then we also have a chance to have a similar exercise, also in wave 2, which would look at something completely different. So instead of choosing between the heat source, people could, for instance, choose between the types of retrofit that they would be more willing to undergo. Or, the idea of heating as a service, the different service types. Any ideas, very welcome, because we have a chance to actually incorporate that over the next weeks or months. And any other general questions, ideas. You might also think about that as a resource that can be utilized going forward, because we plan for that data set to become available for research and for other purposes. So I guess please feel free to talk to us or ask questions now. And I think with that we will say thank you. Thank you. Some references and our contact details. Thank you.
Thank you very much. Very exciting and looking forward to seeing the results. So any questions in the room? Yes, Catherine. And please introduce yourselves. Yeah.
Sorry, my name's Harold Hutchinson. I'm an investment banker in the city, working at the Investec. Is that working now? Yeah. Give me one silly question, just to make sure I understood this. Is this a survey that's being done across the UK? And are you intending to make any regional segregation in your analysis? Because my hunch would be that you might get very different answers to some of those questions depending on where you live in the UK. And the second thing is not really a question, but an observation. My instinct is that this is a long-term question. If we're talking about really serious decarbonisation of heating in the UK, we're probably talking 10 to 20 years ahead, frankly. I just wonder, by focusing on existing house owners, whether you might actually be asking the right question to the wrong people, because surely it's today's young people that will actually really make these decisions. If you look at most markets, it's driven, and consumer choice, it's driven for the first number of years by early adopters. And then mass market adaptation comes through a whole host of factors, cost, regulation, everything else. But I would have thought the answer to these sort of questions, frankly, you'd probably get a better answer asking people around Imperial, rather than necessarily asking a bunch of old people that own houses like me that might be, excuse the pun, a bit fossilised in the answers we'd give.
Shall I go ahead and take this?
Yeah, let's take
Yeah,
this.
there's a bit to unpack there. To answer the first question, absolutely. It's UK-wide, and we want it to be as representative as possible across the regions of the UK. So that's definitely intended. The second point, absolutely. I think this is a constant consideration when we're looking at trying to predict the future. Who should we be analyzing? Whose behavior, whose preferences and choices should we be analyzing? And to be honest, when we're trying to develop metrics such as willingness to pay, where we want people to engage with what is the cost of this versus what else do I have to contend with in terms of my household budget, etc., it's easier to present what are already hypothetical scenarios because we're saying you're considering buying a technology that you know very little about. It's easier to do that with an existing household, whereas with younger people, you can ask them about their preferences, but it's very hard to translate that to a willingness to pay metric. Having said that, I take your point, and so it might actually be interesting to see if we could bias the sample towards younger households, assuming that their preferences will dictate what's happening far into the future and their later decisions as well. So point taken, but there's a reason why we're trying to be somewhat representative.
Thank you very much, Aruna. Thank you.
Question about cost.
Can you introduce yourself?
Sorry, I beg your pardon. I'm Nick James from London. Okay, I'm a private citizen, so I'm not. But I'm interested in electrical vehicles. I used to work in the railway industry. And I believe when we look at electric cars, they're much easier, low-hanging fruit. The economies of scale bring the price down, and they'll be competitive with petrol and diesel cars. At the end of the day, it's cost. As they said to Clinton, it's the economy, stupid. I'm not going to pay 3 times as much money for a heat pump as the gas central heating. We have a cost of living crisis, and unless they can bring the price of these things down, like with electric cars, to a realistic alternative to gas, people, no matter what age they are or where they live, they're not going to pay for it. They're already paying far too much for energy already. And to install an entire system is far more disruptive than a car. A car is self-contained, separate heating system. You have to pull out all the radiators. You basically can't live in your house when they're redoing it. And I just don't see it. It's just for the birds. I know that it would cut carbon emissions, but there must be an easier way of doing it, like using biofuel for the gas boilers, so you can just replace the fuel rather than tear out the whole system and replace it, which would, especially with older people, they're never going to see a return on the investment. If you're double glazing windows, you can see 10 years down the line, they'll pay for themselves in cutting fuel bills. But this, I can't see the return within a lifetime, at least for a lot of citizens. I don't know what the answer to that is.
So to summarize your question for people following online, the question is about the
cost. It's going to cost a fortune.
In case they're not hearing from your mic, I'm just repeating.
Yes, I'm saying for the cost of putting these systems in and running them.
So
in
the
cost of living
upfront
crisis,
cost of the investment into heat pumps.
Yeah. I think, I mean, I don't dispute that. That's one of the reasons why we're doing this data collection. I think the point of this data is that there's a lot of things that we already know. There's cost is one of the biggest considerations. We know that awareness is another big one, etc. So there's quite a few things that we know already about what drives demand. What we're trying to do with this exercise is actually quantify it so that we don't end up, for instance, assuming somewhat not so conservative or overly optimistic, let me put it that way. So we don't end up with overly optimistic assumptions of elasticity, that a cost reduction of X% will be sufficient to make a change. So in order to avoid those kind of finger in the air kind of assumptions about elasticities, we want to get a little closer. That finger is a little smarter than it would be otherwise. And so while I agree, that's partly what we want to try and quantify in this process. So I don't have any arguments with that point.
Thank you very much. I'm going to invite the other questions to happen over coffee a bit later so that we can move to our next presentation. So my colleague, Professor Adam Hawkes, who's a professor of energy systems, and Dr. Sumra Bakaloglu is a research associate at the Sustainable Gas Institute, and they're both in our Department of Chemical Engineering. So today they are going to tell us about how should the UK go forward with, or how far should the UK go with negative emissions technologies. So I think the slides are going to come up, hopefully. They're here, sorry, there. Thank you.
Thank you. Okay, good morning. So I just wanted to introduce this presentation, and then Semra will take over. But just by way of introduction, this is a collaboration amongst 3 different IDLES groups. So it's our own group in the Sustainable Gas Institute, with Semra being the lead researcher. Also, Matthias and Christos Markidis in chemical engineering, and Nixon and Nilesh Shah also in chemical engineering. So this is a collaboration of 3 IDLES groups to look at this specific question. So I just want to provide a little bit of context. Many of you would have seen a figure like this before. This is global greenhouse gas emissions, measured in CO2 equivalent terms on the vertical axis and going all the way out to 2100 on the horizontal. So, as we all know, achieving these climate change targets is very difficult, and it's a very steep tail off of CO2 or greenhouse gas emissions basically from now, and hitting net zero CO2 emissions about 2050 and net zero greenhouse gas emissions by about 2070. So obviously a very big challenge. But the bit we want to focus on here today is that green area at the bottom. So this is actually from about 5 years ago, this figure, and it says gross negative CO2 emissions. So overall, on net, the world is sucking CO2 out of the atmosphere post-2050. But even before that, there will be technologies and measures in place which remove CO2 from the atmosphere. And it needs to be of quite grand scale. If you see at 2100 there, this estimate is around 20 gigatons of CO2 removals by 2100. So that is obviously a phenomenal amount. If you think about total positive CO2 emissions at the moment, around 40 gigatons or so. And then you have some methane and nitrous oxides as well adding up to the total. So that's the challenge here, and incredibly contentious issue as well, because firstly, a lot of these carbon dioxide removal approaches interfere with land use, fuel systems, and broadly sustainability. They interfere with ecosystems because they require a lot of land. Secondly, there's a number of stakeholders out there who will argue that these negative emissions technologies are basically an excuse to keep emitting now. So essentially, we can keep using fossil fuels, keep emitting, and we can just get these negative emissions to offset it and everything will be fine. This, of course, is not true. What needs to happen is both. You need to reduce the CO2 emissions and you need to implement the negative emissions technologies at the same time. So given that global context of this issue, what we want to focus on in this study is kind of drilling down a bit there. So given that we know we need a lot of these, we know it's contentious, we know there's an interplay with reducing emissions, the question we wanted to ask was, how far should a single country go with this type of technology? So instead of the global context, if you just look at the UK, how far should the UK go with these removals and negative emissions? And this is important because A, well, maybe you should do it wherever in the world it's cheapest, is the obvious answer. But this, I think it's much more nuanced, the real answer to that question. The real answer is, it depends on what economic activity you want to keep going in your system, in your country. There are energy security, there are broader security concerns about how you deal with those removals and negative emissions. So that's the big context and motivation for the study. Just one last point before I hand over to Semra is that within these carbon dioxide removal approaches, I mean, there's like 20 of them if you look at the lists in the IPCC reports. Most of them, or a lot of them, are focused on land use, basically afforestation, reforestation, blue carbon, just management of ecosystems so that it can absorb more CO2. But what we want to focus on as an engineering university is the engineering negative emissions technologies. So they are bioenergy with carbon capture and storage, with strong integration with the energy system, and also just direct air carbon capture and storage, which requires energy to operate. So the two engineering-based carbon dioxide removal techniques that have a strong interaction with the energy system. So I hope that sets the stage, and now over to Semra.
Thank you, Adam. I'm going to talk about, as Adam mentioned, we have the different work packages. I'm going to give the brief description for the techno-economical analysis. Before this project, we would like to see what is the techno-economical properties of these direct air capture and bioenergy carbon capture and storage systems, because it is so expensive to capture the air to capture the carbon dioxide from the air, as it is diluted compared to the flue gas from the power station, for example. And we would like to see what is the techno-economical cost of those technologies. And Matthias merged the techno-economical assessment model. I'm just going to present it for the direct air capture today. We also did a similar assessment for the bioenergy carbon capture and storage technologies. As we can see on the figure, left-hand side, we can see that the capital cost of those technologies is quite high, and the solid DAC system is higher than the liquid DAC system. In the solid DAC system, we have a solid sorbent, probably zeolite, that capture the carbon dioxide, and we need a lower temperature to regenerate this carbon dioxide and then store permanently under the ground. For the liquid solvent systems, we generally use the potassium hydroxide to capture the carbon dioxide. And this regeneration process is higher, around 900 degrees of Celsius. And then after we get this CO2, we capture and store under the ground. When we look at what is the cost is breakdown for those technologies, we can see that for the liquid DAC system, the highest proportion of the cost is coming from the heating. As I told before, the process needs very high temperature, and it requires higher heating value. When we look at the solid DAC system, we need higher CapEx and operational costs as well, as the solid sorbent requires more cost. In the literature, the DAX is just in small scale. Nowadays, it's going to get more commonly used, and the cost is changed a lot from $100 to $700 per ton of carbon captured and stored. And we would like to see what is the changes of those technologies before implemented into the national model. Matthias also did the sensitivity analysis to understand the energy prices, energy demand, and the cost of capital impact the overall capture of CO2 amount. When we look at the liquid DAC system, we can see that the system is more sensitive to gas prices. If the gas prices is above, for example, say 50 pound per megawatt hour, we can see the increase in the DAC costs over 500 pounds per ton of CO2 captured. If we look at how is in this solid DAC system is more sensitive to electricity prices, as we can see, but it's not that much sensitive compared to the liquid DAC systems. After we analyze that, what will be the technical operational cost, what is the techno-economical properties of those technologies, we implemented into the UK Times model. The UK Times model is the UK's energy system model that identified the most cost-effective way of achieving the net zero while maintaining the UK's energy demand. And this is the reference energy system. The model is built by the UCL and used with DENS, the government. They used highly for the policy making in the Carbon Budget 5 and 6 report. And we use this model to understand how far we can go after we updated these techno-economical costs in there. In the UK Times, we have 3 supply sectors: resources, trade, processing, and power sector, to compensate the demand from the different sectors, such as agricultural, transport, residential, service, and industry. And we try to understand how we can make those changes to capture more carbon dioxide from air. Oh my God, what happened to my figure? Sorry, it's more, all right. This is the default results from the UK Times model. Sorry for this shape, but the other one is much better. And for this one, we can see that in the net zero policy report as well, it's around 78 to 60 megaton of CO2 is expected to be captured by 2050. Based on the default UK Times result, we can see that the default model captures 78.5 megaton of CO2, but we would like to see what it's captured if we revise these cost values. And we can see that this cost value, it can capture more 105 megaton of CO2, and this is mainly for the biomass gasification for hydrogen technology. And we can see that the system is changed from the biomass gasification to biomass combustion with CCS to biomass gasification for hydrogen because it is a cheaper way to produce. Sorry to figure, I think it's about how the screen is changed. And we can see that after revising the values, we can capture 105 megaton of CO2 more. And we also would like to see how the system can operate under the industrial waste heat integration. And the solid sorbent system is more flexible because it operates at lower temperature. And we know that we have the waste heat from industry, and we would like to see how the waste is changed if we integrate the system with the solid tax system. And we can see that we can capture more carbon dioxide, and it's around 120 by 2050. And this is mainly from the biomass gasification as well as the solid tax systems. We also did the cost analysis depending on the results from the Matthias work, as we can see how far we can capture if this cost of technologies gets lower, because we are not sure how much the cost will be those technologies. And we can see this low, central, and high cost analysis we can capture until 126 megaton of CO2 by 2050. Another scenario that we investigated is what will happen if the demand is increased, if demand is changed. And we would like to see the increase in 25% increase in demand from the industrial and transportation sector. Transportation means the aviation and shipping fuel. Demand has increased. How these negative emission technologies respond to these changes. And yeah, sorry for this. It just confused with, I think, the screen. And first of all, we can see that with this industry integration, we can capture 120 megaton of CO2. After we did this increase in the transportation, increase in the industrial demand, we can capture 122. After we increase the demand in shipping and aviation, based on the biomass strategy of the government report that recently published, we are expecting more demand in the aviation and shipping fuel, and we can see that we can capture until 126 megaton of CO2. The main technology is the yellow line, and you can the biomass gasification with CCS, and we can see that it's pretty constant when we increase the demand because of the biomass availability, that the biomass technologies cannot go further. If you look at the purple one, which represented the solid tax system with industry integration, we can see that this solid tax system is flexible and go further for when we increase the demand from the transportation sector. After we get the results from overall UK energy system modeling, we would like to see how the things is going on in the industrial clusters, because the purpose of this project to understand the industrial integration impact in the solid tax systems. This is a map of the UK industrial clusters, and we can see that the industrial clusters, there's a different sectors, the heavy industries and light industries, from cement, chemicals, petrochemicals, paper, food and drink. And the most interesting thing is that these industrial clusters have the synergy that we can get the benefit. For example, they can use the same carbon capture and storage infrastructure. They can get the benefit from the centralized fuel production, or one of the waste from the unit can be the feedstock for another unit, and we can understand how this different industries can work with together. And according to how willingly each industry take a risk, we can get the prioritized solutions, depends on their sharing with the stakeholders. And for the industry clusters, Nixon Sunny did the study, and he chose the Humber region. The Humber region is the biggest industry clusters in the Yorkshire in terms of the carbon dioxide emissions. It emits 10 million tons of CO2 per year, which is the 2% of the UK's total greenhouse gas emissions. And in this Humber region, there's different sectors. We can see this iron and steel refining sectors. And the government has also the ambitions for the Humber region. The Zero Humber Carbon project is going on to get the zero emission by 2040, being the first of the world zero emitted industrial clusters. And Nixon assessed how would be the energy system in these industrial clusters in the cost-effective way. And according to his models, the heat combustion with CCS can capture the process emissions, and the system is shifting to the hydrogen, and the blue hydrogen generation is the main contributed than the renewables and the biomass gasification with CCS. He also gets the similar results if we have the more available for the biomass gasification. The system is more willing to switch to the biomass gasification with CCS to produce the hydrogen. And we also see that there is also 3 to 15 terawatt-hour of waste heat is available from industrials. In the UK Times model, we can also estimate a similar waste heat that can be used for the solid dark systems. And in order to further investigate for this biomass availability, we also assess how this cost avoidance is changing based on the availability of biomass. First of all, the system chooses the biomass gasification with CCS, called as BHCCS, instead of DAC. But if it is more available, the cost of avoidance is go down, and it switch with the blue hydrogen. If there's more biomass availability, it also switch with the post-combustion with CCS. You can see the orange cross, and it also shows us that if the waste heat is used by the DAC system, it lowered the cost of carbon avoidance by £50 per ton, which is also similar in this national model as well. To wrap up this presentation, I can say that for the default cost, the UK Times tell us that we need at least 78.5 megatons of CO2 by 2050, but we can go further after revising the costs, and with this industrial integration, we can capture 120 megatons of CO2. With low-cost analysis, it could be up to 126 megatons of CO2. If we consider the increase in aviation and shipping demand, we can capture more 135 megatons of CO2 with low-cost analysis. And when we look at the industrial cluster side, we can see that the negative emission technologies in industrial clusters a significant increase the carbon dioxide capture, and depending on the biomass availability, we can capture more, and this biomass gasification with CCS for hydrogen generation is chosen over the biomass combustion for electricity generation. And I would like to also thank you for IDLES and my co-workers, Matthias, Mersch, Nixon, Professor Christos and Professor Nilay, and Annie for our master's students. We would like to hear if you have any questions. Thank you.
So any questions from the audience? Yes. There's, and don't forget to introduce yourself.
Yes, it's working, I hope. I'm Marco Pantaleo from Imperial, and I wonder if you are considering the use of CO2 to decarbonize industrial supply chains. So CO2 can be transformed, instead of being sequestered, can be transformed into a valuable chemical feedstock together with green hydrogen, or so this is a typical example of sector coupling. and use CO2 instead of sequester it to produce steel. So we store carbon for a long time, or other options. Is this possible? Has this been considered, or in the future can be considered? So demand of CO2 to decarbonize supply chains.
We consider for the carbon dioxide storage. It can be also utilized. Actually, when it's utilized, it can also emit it during the process. It cannot be totally negative, maybe the neutral. When using this carbon dioxide during the process, you can emit in during the process. But to just totally focus on for the negative emissions, we focused on the storage rather than the usage. But yeah, you can use, especially for the industrial clusters, you can use for these other units. It can get more benefit. We can explore in the future, yeah.
Technologies and innovation are exactly there,
Yeah.
to transform CO2 into carbon useful for industrial supply chains and so on.
Yeah. Thank you.
Thank you. There's a question. I'll start at the back over there. And then we might have time for a last question there.
Hi, Luke Hatton, Imperial College. I've just got a quick question. You mentioned the cost of capital is quite sensitive. The cost of carbon avoidance is quite sensitive to the cost of capital. I might have missed it in your slide, but what assumptions did you make over the sort of sensitivity? Like, what range did you look at?
You mean the techno-economical cost or the industrial cluster one?
The techno-economic cost.
Techno-economic cost for the, Matthias maybe answer questions. Yeah, he did my analysis.
Thank you. Yeah, no, you got a good point, because basically all these technologies, especially DAC, are very capital intensive. So we just wanted to look at, the influence of different, cost of capital. And I think we looked at anything between 5 and 15%, where, the lower end would probably be something that's backed by the government and, something that they might be able to achieve, and the other end might be, something you would find on the, in the private sector, in the open market. But yeah, it's not really based on any financial analysis behind this. We just wanted to see the effect of considering a range of these.
Thank you very much. There's a question, and it will unfortunately be, yes, we have a bit of time left. Another question here, please.
Equinor.
I think the microphone might be off. No, it's on now. Thank you.
We hear from Equinor. Can you hear? Yeah, I have two short questions. First is this negative emission technology. How percentage this compared to the emissions? Do we have negative emission technology can account 10% or 20% of the total emission percentage compared to the total emission? The second question is the cost. This negative emission cost per kilo or per ton of this CO2, which you can capture, compared to the CO2 emission reduction, just in general, and how the cost comparison. Thank you.
Thank you. So there's a question about the percentage and about the cost, maybe Adam.
Is this on? Yep. So I think the first one, if you look at UK only, the percentage that negative emissions, it has to totally cancel out the positive emissions for the UK to reach its net zero target in 2050. So it's 100% of positive emissions for the UK alone to hit that target. If you look at the world, it's a different story. Actually, the negative emissions are more than the positive emissions. And that's why you have net negative emissions beyond 2050. So 200%, 300%. So very substantial numbers. The second question was about the cost of abatement. The model we've used here, UK Times, basically equalizes the abatement cost across all the options. So essentially, if it's adopting this technology, it means that the marginal abatement cost of that technology is the same as the cost of reduction of emissions in the system. So if we see here, say, 300 to 500 pounds a tonne, that is the actual cost across the entire system. So it's not just for that technology.
Okay. Thank you very much. Any other question? No, so thank you very much to both of you for a great presentation, and I'm sure it will spark conversations at lunch. So we're now going to move to our posters, and we're going to have a few introductions to these posters. So Catherine is going to chair.
Thank you. So during the lunch break today, we'll have the opportunity to visit the posters at the back and discuss with the authors, who are researchers and students in the IDLES programme or from closely affiliated projects. So some of the authors have prepared a short pitch of their poster to put to you now ahead of the lunchtime discussion slot. So they have an individual slide each with which to use. So we'll go firstly to Matthias. So if the other speakers are able to come down or in this corner so that you're able to be called up quite easily.
Thanks. Yeah, hi, it's me again. I'm Matthias. And this is the poster which I like to call Everything You Ever Wanted to Know About Heat Pumps, which is obviously, a bit of an exaggeration, but in the group we've done, and this started with Andreas, who gets a lot of credit. He's sitting there, Andreas Olympius, and also Paul Sapin, and with Professor Christos Markidas. We've been looking at heat pumps from many different angles. So Andreas has done a lot of work on the system itself, optimizing the heat pumps, optimizing the operation, optimizing all the components, and then also looking at how does it integrate in a building, how much storage do we need, how do we optimally operate the thing. And then we've also done quite a lot of work on the other side, which is, in the spirit of IDLES, we looked a lot at whole systems and the impact of widespread heat pump rollout on the energy system. Where do we get the electricity from? How does it compare to other heating technologies? How much can it contribute to the decarbonization of the country? And then also how much, given that our electricity is not yet carbon-free, how much are we actually already saving today in terms of emissions? And then we also looked at the integration. This is, again, Andreas looked at integration. How do you design heat pumps with the system in mind? Because you might see different designs if you purely look at the households or if you look at the whole system. And yeah, anything that you're interested in, we're more than happy to answer the questions at the poster. Thank you very much.
Thank you, Matthias. So next, I believe it's Jacek.
Okay, hi everyone. It's also me again. So this is a piece of work that was undertaken by our former PhD student, Heather, who's now back in China working for the industry. But in her PhD research, Heather was looking at the issue of trying to model building occupancy using Wi-Fi data that we managed to gather from across the college. But the underlying hypothesis is that if you're able to predict the occupancy of the building, then you're able to run your systems more efficiently, primarily through better HVAC systems use. Now, the bit that was novel in her work primarily is the fact that she did not treat building as an entity that exists in an isolation. Quite the opposite. Building and building's occupancy will be affected what's happening in other adjacent buildings. So simple example, when the lunchtime comes in and people leave from a lecture theater, you can expect that sort of that decrease in occupancy will be seen as an increase in occupancy in, for instance, the canteen and things like that. That was the first idea. But then subsequently, she went even further, and she started looking at how to model existence of buildings or groups of buildings within the wider fabric of a city. So for instance, if there is a tube disruption, can we expect that the arrival and departure patterns and the overall volumes of people will change in the buildings by incorporating suitable variables based on the data that is coming from the urban environment. So she managed to integrate the sort of occupancy model with a agent-based activity travel simulator. So effectively, what's happening is that you're able to simulate, you know, people's daily travel diaries, so you know when they travel, how they travel, and that is then linked to building occupancy models. So you know people depart from their homes, they travel for a certain time, then they arrive at the building, then they move around the building, and then they leave it, and then they go back home. The idea being is that you know that allows you to kind of model the links between things such as lifestyle disruptions on transport network and so on to what's going to be happening at the building, and therefore how you should run your HVAC if you know what's happening around the building and in the city. If you're more interested in that, you know, please feel free to sort of approach me in the, during the lunch at the poster, and that's it. Thank you.
So next we're going to hear from Han.
Hello everyone, I'm Han Wang, a PhD student in Civil and Environmental Engineering Department at Imperial College. I'm excited to share with you my research about improving machine learning-based load profile modeling by assessing different methods and developing applicable guidelines. So load profile generation models are pivotal in residential energy demand modeling and demand side management, as they can provide daily electricity consumption profiles based on human activities. Traditional bottom-up methods usually establish linear relationships, such as constant conversion factors between activity type and energy consumption. However, the energy consumption of activities is also influenced by other factors, such as the timing of the activity, the electricity price, the interaction between simultaneous activities, and the social demographics. In addition, machine learning models, while popular in nonlinear prediction problems in other domains, are rarely employed in this domain to generate residential electricity consumption based on human activities. So to address these gaps, my research assessed 6 machine learning-based load profile generation models and provide applicable guidelines by designing 3 groups of test scenarios. Specifically, we analyzed the impact of 8 sites of input features, 4 widths of historical time windows, and 2 trend test split methods. The result shows that integrating energy prices, activity-related features, and social demographics can improve the prediction accuracy. And combining historical electric consumption records with activity-related features will make the model performance more robust against the sudden load variation. And in this multi-household residential context, algorithms like light GBM and artificial neural networks outperform other machine learning algorithms, such as long short-term memory and support vector machine. In addition, the questions in the title of this research and this slide is also answered. There are 3 contexts when it is worth combining electricity demand data with rich information about household and their activities. First is when the output of energy demand models are utilized in demand-side management associated with indoor activities. Second is when the sudden load variations appears in the residential electricity consumption. The third one is when the load energy demand modeling is used for targets that has less historical data, or when the target is quite different from the training data set. This research has been published in a journal paper in Energy and Buildings. So if you are interested in the detail, please, I invite you to explore the full published paper or approach me in the conference. Thank you.
then finally, Eamon is here.
Thank you, Catherine. My name is Eamon Mirza Beg, and I'm a PhD student in Electrical and Electronic Engineering Department, supervised by Professor Goran Sterbeck. Today, through this research, I will emphasize on the importance of zero-carbon ancillary services in future electricity grids. So the two challenges that will be addressed through this research are that the future will be, the system will be characterized by reduced levels of inertia, and this reduced levels of inertia will in result increase the requirement for frequency response services that will increase the cost for ancillary services in the system. So the main aim of the goal is, the main aim of this research is to co-optimize these ancillary services into the stochastic unit commitment model. And for that purpose, we used inertia-dependent frequency security constraint stochastic unit commitment model. And the objective function of the model is to reduce the overall system operation cost while guarantee that there will be enough ancillary services within the system. So the frequency security constraints are obtained from swing equation that represents the dynamics of electricity grid. And then the ancillary services are from inertia from synchronous condensers and frequency response from renewable energy sources are then mapped into the optimization through the frequency security constraints. So for the analysis, two strategies were considered, which we named as TS, the traditional strategy, in which we do not co-optimize ancillary services from zero-carbon sources, and the proposed strategy, which we named as PS scenario, where we do co-optimize ancillary services from zero-carbon sources. So these strategies were analyzed under two different wind capacities, 70 gigawatts and 100 gigawatts, and the results at the top left-hand side demonstrates that the ancillary services, the cost for the ancillary services and the energy-only market. So the results show that when the wind is 70 gigawatts, the cost for ancillary services is 35% of the total system cost. However, with the proposed strategy, that is co-optimizing inertia from synchronous condensers and frequency response from renewables, we can reduce this cost from 35% to 3.3% of the total system cost. And however, with increasing wind capacity to 100 gigawatts, this cost for ancillary services further goes high to 45% of the total system cost, which can be reduced to 4.4% by co-optimizing zero-carbon ancillary services. And to further analyze the impact of zero-carbon ancillary services on emissions, we further conducted some analysis in which we showed the emissions due to stability actions and the emissions due to energy production. And the results demonstrate that the emissions are very high in the TS scenario, whereas the emissions can be reduced in both the cases. When we have wind capacity of 70 gigawatts and 100 gigawatts, we can reduce these emissions significantly through our model. Thank you.
Thank you, Eamon. So now I'm going to invite Tim to come back up. We've got our keynote address coming up with Carolina Tortora.
So actually,
who's over there? Yeah.
Ah, right. Okay. Actually, I think we missed the chance to give those poster presenters a quick round of applause for those highlights. So we've run slightly ahead of schedule, but very grateful that we have Carolina Tortora with us. So I know she's had to come from another engagement with National Grid this morning, so very grateful you could squeeze this into your busy schedule. Yes. No, please. Carolina heads the Department of Innovation Strategy for National Grid's electricity system operator. Prior to joining ESO, she had a similar role in Rome with the Italian transmission system operator, Terna. And amongst the various projects that she delivered there was, at the time, Europe's largest high-voltage connected battery energy storage system. So she has some very impressive real-world experience of delivering large innovation projects. And we're delighted that she's joined us today and is going to discuss the role of digital technologies in helping tackle the energy challenges. Thank you very much indeed.
Thank you so much. All right. Hello, everyone, and I'm really sorry because I'm right before your lunch break. And it's a keynote speech coming midway. So first of all, why I wanted to come here. Number one, I haven't really done any university talks in a while, so it's always a good idea to kind of recenter the geek soul within all of us innovators and try to see what's going on or how to attract the right type of thinking into the field. So I'm really glad to be here. You'll be happy to know that Imperial did not accept me when I applied back in high school at the time. So I ended up going to the university, so I do have a chip on my shoulder. But, you know, gotten over it. It's been enough years, so hopefully you'll accept me now. All right, so today, when talking to my team about what the topic of the presentation would be, the reality is, as you can imagine, you know, there's a lot going on in our innovation portfolio. We've got about 100-something projects, and I got a lot of money to play with, right? So Ofgem approved us over £50 million worth of innovation budget for the T2 period. That's the regulatory period for a regulated business like the national system, like the electricity system operator. And that's more than any other network out there. So that's a lot of money to play with. As a result, we do have, you know, we are funding a lot of different projects, but there's a lot to tackle. There's a lot of problems that we need to look at. So out of all the projects, we needed to find a focus for today. And, you know, it seems like digital is kind of like the dish of the day. This seems to be where most of our efforts are going, so that's why we decided to go into it. So first of all, what is the system operator and why do we exist? So we've got it down, like this took many meetings and many consultants to get it down to 4 high-level bullet points. The first, we need to ensure a reliable and secure system operation. So we need to be able to deliver electricity to consumers when they want it. 2, we need to transform participation in the sustainable markets. So this means that we run power markets for the UK, and we have to build new ones as the system transforms. 3, we need to ensure that we get the right value for consumers. This pretty much means you need to do it at the lowest possible cost. And 4 is all of this is while we drive towards a sustainable future, a greener future. A lot of today's presentations has focused on some of those challenges around that sustainable future and what it means to tackle it. Well, we're the ones who are kind of driving the whole agenda for the UK right now. You know, 4 jobs goes alongside another mission, which is, again, more hours of meetings and more consultant work to say that we have a mission, which is we drive the transformation to a fully decarbonized electricity system by 2035, net zero by 2050, of course, if we still hold that, which is reliable, affordable, and fair for all. So what does this mean? I don't know how many of you have heard of the energy trilemma. Essentially, we usually say, you know, there's pretty much 3 things that you're playing around with. You are trying to get energy security, which means you need to have enough generation to meet demand. That's only the beginning of the story, right? Because security means that that electricity generation has to be secure, not just from cyber attacks, but from all the physical problems that come from it coming from renewable energy and so on and so forth. You gotta be sustainable. You know, I've got a little kid. He thinks my job is saving the world, which is a huge upgrade from when he thought I was an electrician. So I'm happy that we're there. And essentially, I'm trying to build a greener future for him. Like, I find purpose in what I do. And of course, all of this, you know, electricity bills going up, this is a very current kind of situation. All of this has to be done in the most efficient possible way. So this is a trilemma because you cannot really solve for all 3 of them. So you're all likely all engineers, so you're solving in time and you're solving depending on what kind of situation you're dealing with. You could do system operation the Johannesburg way, which is, 4 hours of blackout every so many hours, but I don't think British people will be okay with that. So here is an idea. I insisted on this slide to give you like a snapshot of the scale of the kind of issues that we're dealing with. We're the system operator. The United Kingdom runs a transmission load which is around 300 terawatt hours per year. That's huge, right? You have a peak demand which goes around 50 gigawatts, so you're dealing with huge amounts of energy moving every moment in real time. How is this changing, right? So we're going from a world which was quite straightforward. You had 140 or so thermal generators, big ones, that are generating coal, those smelly, noisy, clunky, old school generators that are generating electricity on one side, and then you have one-way electricity going down, all the way down to consumers. Now the world has changed. You're getting over 150% increase in wind generation. That's just in the past 4 years. My background is actually aerospace. Aerospace moves relatively fast. This is an industry that hasn't really advanced in ages. You still have transformers on the grid from the 1960s. It's not because they're lazy, it's that it was okay, right? So it's a stupid machine. It does one thing only. It doesn't need to be upgraded. So this is a huge change for this industry, 4 years. Interconnector capacity has gone doubled. We've had 4 new coming in. The latest figures I've seen more than 20 gigawatts coming in interconnector capacity for the UK. And interconnectors come with their own, they're a solution, but they also come with their own wealth of problems. And you're changing the type of balancing actions you're taking. Balancing actions is really what the electricity system operator does, which is how do you balance, how do you manage that last second, that final mile, when generation does not exactly meet demand? Who do you dispatch in order to meet that, to get that net zero? Because it is a zero-sum game, right? Over 65% of them are going to small ones. So it's no longer your 500 megawatts, your gigawatts of nuclear power plants. You're actually dispatching wind farms. You're dispatching solar. You're dispatching batteries. You're increasing the number of market participants, which increases complexity. There's way more BMUs. As I said, there's an increase in numbers of balancing. BMU is a balancing something unit. I forget. You have, I saw a presentation earlier as well that is looking at, some of those stability issues that we're seeing. With more renewables comes decreased inertia. Presentation earlier said that I did used to work for the Italian TSO, so I thought that Italy was facing some big problems when it came to stability and, the increased penetration of renewables and solar and whatnot. But it's not an island, right? So Europe has the incredible support of French nuclear power plants to stabilize the system. Here is an island, We used to think of National Grid back in Europe as cowboys, because you got frequency excursions here, so you wouldn't dream of seeing in continental Europe. And that's decreasing even further. You're getting decreased reactive power capacity, more complexity in system operation. Balancing actions are 50% of demand. So instead of being an adjustment of, we're almost there, we only need to, dispatch up or down so much. Now it's 50% of demand. Again, that's a huge number. And we are increasing the number of interconnector trades. So we went from 3,700 to over 53,000, and a huge increase in balancing and constraint cost. To give you a clue, so pre-pandemic, we spent about £1 billion a year in services and balancing action. That's high. Okay, that's not low, that's very high. This year, we're looking at almost £5 billion in balancing costs. This is 5 times as much. By the end of the decade, and this is a number that I just got this morning, we're looking at almost 8 billion, unless we come up with something or we figure out a way to, new services, new resources, and whatnot. Another thing that I found out this morning is that Monday we actually had a record. We beat our own record of how much renewables we had. So we managed to hit 57% renewable energy in the UK, Monday, 2 p.m. So the situation is evolving, right, and it's becoming more and more complex. Sorry. So here comes my job. And I've been told recently that I have the coolest job, I don't know if in the world, but definitely in the company, where I run innovation, all of this. I am literally paid to solve problems and to spend money. So the definition of innovation is to look at higher risk activities, which is ironic because almost everything that is happening right now in the business is innovative and new. There's no engineering books written about how the system behaves in these kind of numbers and this kind of situation that we're dealing with today. We test, develop, we use our ingenuity to come up with ideas for projects to address some of the issues that we're dealing with. And we do this, and we have been doing this through a publication, a yearly publication of innovation priorities. So what we mean by this is just that where are we focusing our firepower? Because there's a lot going on. This doesn't mean that these are the only issues that we're dealing with, but this is where the money goes, okay? Now there's 6 priorities, and we started with something like 13. I've got it down to 6. Fintan, my CEO, is telling me that if you have more than 3, they're not really priorities. I disagree. We have the money to play with it, but essentially these are it. This is where we're looking at this year. And it's, as I said, it's a live thing. Priorities or strategies should be alive. That means that you need to be able to go back and change your mind. You do have the ability to do that. But right now, this is what we're looking at. The way we're addressing the problems is through doing some horizon scanning. So what are the solutions and technologies out there? We do a lot of open innovation. We engage externally, me being here as an example. We have a very healthy innovation portfolio, and we have a bunch of high-level strategic programs to address them. Today, as I said, we're going to be focusing on the digital and data transformation piece. Here are 4 main areas of what we mean by saying that this is a priority, and what are the areas that we're looking at. So one of the big things for us is data and transparency. So the ESO, as I said, we run markets, we manage the grid. The way we do this is through modeling. We are a technology modeling company. This is it. It's like we are a Vegas house, and the trade is here models of things. We need to understand what's going on. The rest of the market is trying to bring down the house. So we need to always be a step ahead of everybody else. All our models have to be better. And for them to be better, the only advantage we have, aside from the fact that we've got some of the best brains in the business, at least my team definitely does, is the fact that we need to have access to more data than everybody else. So data is the big thing. Transparency and understanding. Transparency not just for us to come up with the right tools, but transparency also for the market to be able to give the best services possible so that we always have what we need when we need it. The digital and data area, of course, cannot prescinde from cybersecurity. You might have heard, I think every day you open the news and there's an article from our CISO, Simon, so he's our head of security, who tells us of some company somewhere in the world who got cyber attacked. It's like, you see, change your password. There's more to that, of course. It's about being sure that we are secure, that nobody can break into our systems. It's about consumer choices. So we need to understand how consumers behave so that we can cater to what they actually need and not give them any more. Future is a margins game, meaning I'm going to give you exactly what you need, and thank God I can do that much, because probably I won't be able to afford, or you won't be able to afford anything more than that. And to do all of this, you need to unlock flexibility in the system. Flexibility is a word that encompasses a lot of stuff. Many of the presentations you guys discussed today. Flexibility is the ability to move the market up, down, so that you can meet generation, and you can respond to stability issues, frequency constraints, and so on and so forth. How do we do this with digital technologies? So there's a few of them. Machine learning, so AI in general, digital twin technology. And of course, we're doing some horizon scanning, looking long-term at things like generative AI and quantum computing. So now I think, yes, I will discuss 4 projects that the teams have been working on in ESO to give you a sample of the type of work that we do. So CrowdFlex, we just got this funded. So I said we do have over £50 million in NIA. NIA is Network Innovation Allowance. That is completely within ESO's control, aka my control. So we fund projects depending on whether or not we feel they're appropriate for the grid. But we also have access to something called the Strategic Innovation Fund, which is a £450 million fund held by Ofgem. Ofgem is the regulator. They're the ones who pay us. who, it's a competitive process, but, and it takes a while to get there, kind of like Horizon 2020 sort of scale. And this is a 22 million pound project. So this is the largest one that ESO has ever led on. What Crowdflex is trying to do is really, it came from an idea. So here you have the entire energy market. You have generation and you have demand. Everything we do is to control generation in some way. So we're trying to limit it. We're trying to understand how it contributes, how it doesn't contribute. We build services. We've got over 20 different services in the UK market. 20. In Italy, there's 3. So there's 20 depending on who you are, what your power output looks like, how fast you can ramp up, how fast you can ramp down, how accurate you are in hitting things. It's crazy. And we're not touching demand at all. So there was the idea, how can we possibly ignore 50% of the market? That makes absolutely no sense. If you're going to have a future, sustainable future, we're all playing this game. Everyone has to have a seat at the table, so we need to understand demand. The problem is that we do not understand demand, and domestic demand in particular. So as an engineer, what do? You black box it. And I'm going to characterize it as well as I can. So you shake the box. So we came up with a project idea, which is really just trying to come up with a utility function for people. So we're going to be trialing different services. What happens if I buy it? If I ask you to do your laundry, like in a week at 4 p.m., how many will say yes? How many will say no? How many will do it at 4:05? How many will do it at 4:01? So it's turn up, turn down demand, and seeing how firm, because this is an actual term in services, firm response, how firm your response would be. So we're modeling this. We're using AI to try and simulate it. And we're working with a bunch of the same customers and energy companies that you guys know very well, your OVO, your Octopus, OMI, electric chargers, and Alexa, to try and see if we can build a rapport with consumers of energy and see if we can build better services for the future. Solar nowcasting. Yes, we do have solar in the United Kingdom. Doesn't seem apparent today, but it does happen occasionally. So the problem with this is that, as I said, transparency, we're blind. Anything that happens below our substations, we have no idea. But the reality is that it's not just our DNO, so our distribution network operator partners' fault. They don't know who has a solar panel and where do they sit. So in comes a startup that says, I've got an idea. I'm going to look at pictures from satellites, and I'm going to have output coming from the DNO substations, and I'm going to overlap these two things, so I'm going to know where the cloud covers are, and I'm going to make an assumption as to what solar panels there are. Seems quite straightforward. So when I pitched this to my CEO, he was like, aren't we already doing this? It's one of those, like in Italy you have an expression which is Columbus egg. Once one person does it, everyone says, okay, fine. That was easy. Well, it wasn't. So these guys have been doing it, and that improved dramatically our forecasting ability. So this is an idea, again, of how digital technologies or how looking innovation out of the box can support our forecasting ability. Perfect to talk about dynamic reserve setting now. So why do you want to become better at forecasting solar, wind, and so on and so forth? Well, because part of my job is I pad the grid, right? So when I set reserves, it means that if there's a demand of 60 gigawatts on the grid, I need to be able to meet it no matter what. So I need to set myself reserve. So I need to have enough power so that if I lose a nuclear generator, if I lose an interconnector, there's different ways to calculate this. You usually have the point of biggest loss. There is a combination of losses. You have to build resilience in the system, and that's what the reserve does, really. But even though our ability to forecast has improved dramatically, we haven't really changed our reserve. And the reserve should change with our confidence, right? So the more confident I am in my forecast, the less reserve I need to hold. That's the whole point. And this is a big number for us because this means money. The smaller the reserve, the less money I spend, the less money you have to pay on utility bills. So how do we do it? Machine learning. So depending on the combination of renewables you got or the energy mix of the day, we will set a different reserve, which will be directly dependent on our confidence in that. So this is going to bring actual savings to all, hopefully, one day. Advanced dispatch optimizer. So this is a project that we've developed with Google. Google Tapestry, there's Google X, actually, sorry, they're called X. So essentially what we're trying to do here is inspired by Google Maps and the ability to have real-time imaging of what's going on in the world. We wanted to build a digital twin of the energy system. More on that later. But ultimately, we needed to find use cases for it. And the biggest use case that we have is a control room. As I said, £1 billion 4 years ago, 5 billion today. Any improvement I bring to this world means a lot of savings for the whole energy system. Think of the scale, £5 billion. Yes, it's a lot of money. So what we're trying to do here is essentially, can we use digital twin technology in the control room to make better decisions? The way the control room works today, and I invite all of you to come and see how our colleagues work in the control room over in Wokingham, is essentially we make models, as I said. We have models that span, there's some colleagues that are looking at 30 years ahead, FES, future energy scenarios, all the way down to real time in the control room. Models get more and more sophisticated or more simple, depending on how you see it, as you get closer to real time. But it becomes more and more complex for control room engineers to get all that information. So I've talked to them, and they'll ask me anything from, Karina, can you get me a robot? Or 100 robots in the control room, so I press one button, and 100 robots press 100 buttons, so they're dispatching 100 wind farms. So that's clearly not a good idea. But what I can create is essentially a scenario-based optimization of the control room. So that's what this project is trying to do, is breaking down the problem. Instead of bringing everything to real time, I'm going to break it down into different phases so that the only thing you need is the final decision in the scenario. You have 2 or 3 scenarios from which the control room engineer can pick. And that's what we're trying to build here. So simplifying is a very engineering approach, probably it's simplifying by breaking down the problem, setting the system at different times so that your biggest budget, which is computational power in real time, is saved as much as possible. I mentioned digital twin. So when we started on ADO, and my CEO wanted me to build a digital twin of the whole energy system and put it in a computer for him in Wokingham, and I'm not joking, okay, like seriously, that's what he expected. We ran into a big problem, which is data, and the fact that we do not have access to data from the whole system. Not only that, but can you imagine, so I went to State Grid of China to see the one digital twin they had of a single interconnector. One interconnector digital twin that could do simulations all the way down to EMT, so real time and really detailed transient simulations. And it turned out that this thing was as big as this building. It was all, computing power, just to simulate a transient. So imagine doing that for the whole energy system. That's impossible, right? Definitely cannot put in a single computer, not today, not with today's technology for Finton. But what I can do is federate it. So everybody will have a digital twin of something, right? Whatever they're coming to the grid with. I'm going to try and connect them, like an internet of digital twins, essentially, where all I do, well, not all I do, because it seems like it's simplifying things, but it really isn't, is standardizing the way that this data get exchanged so I can tell them what data needs to be exchanged at what time and give me access to it when needed. So this is a virtual energy system, and this has been the bane of my life for the past 2 years. We launched this at COP26, 27 was it in Glasgow? I forget which number that one was, but it's been intense since, because trying to get the industry to agree is almost like corralling sheep into a direction, so that's kind of been what we've been dealing with. So these are some of the existing projects that we've been dealing with. Now very quickly, I'm going to move into the next part of the equation, which is fine. So this is the existing technology. This is what's going on today that we can use. But are we really doing our job if we're not looking for what's next and we're not keeping our ear on the ground to understand what's happening? Enter technology horizon scanning. So this is a brand new function that we have. And as ESO evolves into the future system operator and we start picking up gas, hydrogen, heat, and so on and so forth, our responsibility grows. Whole system means that you need to start looking beyond the simple confines of your energy vector. Call it vectors and sectors. To do this, we need to understand what are the best technologies out there. what should we be looking out for? What should we be looking out not just as a solution, but as a potential threat for us, so that we can inform the rest of our colleagues' decision making and inform them, there's a solution coming for you. So we've got two today to really tell you about that we are interested in so far. One, of course, is quantum. We feel that the particularities of quantum computing may adapt really well for scenario-based modeling or multi-decision making ability that we have to deal with within the ESO control room. So it feels like it's a good match for us. We understand that it's very early, so we've attended a few conferences. We've been talking to universities and other technology providers to understand whether or not there is an opportunity here, and if so, where is it? And when will we be able to use it? But it feels like it's a bit longer term right now. The other one is, I think you're all sick of hearing it, which is generative AI and what it can do. Now, the reason we're interested in generative AI is that essentially one of the problems or one of the limitations of machine learning or neural network or AI in general is the fact that it needs data. So you need to train an algorithm with data so that it can make predictions. The problem is that the data that we have, when it's available, it's based on a system that is ceasing to exist. So it's not really giving you much, right? Because the information you have is on an old system that we don't have anymore and that will continue to evolve in the future. Generative AI has the tremendous ability to allow us to generate new data. So it's a combination of things. Not only that, but it allows us to then do more complex sort of thinking. We're thinking of applying it, for example, in network development. So one of the new things we're picking up with the FSO is actually around the ability to design long-term for the system across different vectors. So how do you make a design for the future UK that has gas, electricity, and hydrogen in one single design, while taking into account demographics, development of cities, roads, and everything else? Well, that degree of complexity is very hard to put on a single one of our engineers or even on one of our Plexus modeling software, right? So we feel that generative AI may have an opportunity here. So we're looking at different use cases. Again, we're working with universities and we're working with other technology providers to see if there's something to go on here. And then wanted to close the talk talking about the AI Center of Excellence, which is really one of our most strategic programs at ESO. And it's a big deal for us because we realize that a lot of the work we do, we're always thinking about the tools to do this and the tools to do that. And if you look at our business plan as a company or of any network company right now, you will notice that at the heart of all of this is the people, the talent to be able to run these technologies and to really do the job. And we are having trouble to attract this talent and to get it. Again, this is why I came here, because one of the things that I've been told going to conferences is, well, I didn't know that I could work in decarbonization. So I worked at Photobox in organizing freaking holiday pictures. No, right? So there is clearly an ask here, and we need to be able to work together in order to ensure that we get the right talent in the professions. And that's also part of my job. How do I solve this for the future? So one of the things that inspired me really was back when I was in the US, there was such a thing called the ROTC program, which is a very similar problem to what network companies or utility companies have here. The military has in the US, which is they need doctors, they need engineers, but they just can't afford them. A doctor in the US can make more than $500,000 a year. Military will pay them $30K. So how do they get them? So they go to universities, they work closely with universities so that they help support them throughout their education, and then they lock them in for a few years. So I was in aerospace, and I had a few of my classmates that were pretty much coming to class with me in the morning, and then in the afternoons they would have like raising the flag, boot camps in the weekends, and they were always having these incredible internships in the summer in a submarine or in rockets or something like that. So pretty cool stuff. How do you transfer that here? So the idea is, can we create something similar in the UK where we work alongside professors in academia to try and preach the verb, right? So try telling them, we need you here. This is an area that is going to become huge. And, you know, almost like the church, this is a purpose-led job, right? So you go back home every day thinking, I'm doing something good for the future. This is really what we're trying to do. So the vision is really to work alongside academia so that we can influence some of those courses that are being taught so that they understand how the disciplines of what you're studying can be applied in the decarbonization world. We want to promote collaboration with private companies, so we are working with your Googles, your Octopus, your Amazon, so that we create cross-internships. So you spend a few months in each one of these companies, you learn to solve the problem from different aspects. So you see what does it mean to solve the decarbonization problem or to face a decarbonization problem from the perspective of a EV charger or a aggregator or a generation production, or from the system operator perspective. And then, you know, so you are working and studying because you are actually delivering programs and tools for us. You're also creating a way for us to exchange resources. So we're working also with Carnegie Mellon in the US to see if we can exchange learnings and so on. And finally, to work together in a lab. So it's a safe environment where you can actually test drive those same tools, AI tools and stuff that you're working on together. So that was it for me. Sorry for all of you taking pictures today, but you can take a picture of our dinosaurs, where you'll see how to get involved. By this, I mean how to actually bring a project to our attention in the innovation team. We do have a lot of projects with Imperial College, always hungry for more. There's a view to our annual publications. We've got annual summaries and stuff where you can, you know, see more of our 100 and so portfolio. A bit more on the virtual energy system, so the data sharing framework that we're trying to build across the whole energy system. And of course, last but not least, how to work with us. So internships or potential graduate schemes or, you know, full-time employment at ESL. That's it. Thank you.
Well, thank you very much indeed, Caroline. That's absolutely terrific. I love the slide where you walked through all the things that have changed and how much they've changed, and then a whole series of slides of the things that are coming up. And there were so many highlights in there, I don't know what to pick out, but one was this idea that data-led modeling and the modeling work we do tells us what we've got for the system of today. But really, that isn't what the exam question is. The exam question is, what's the system of the future going to look like, and how do we optimize and control that? Anyway, you didn't come here to hear from me on that. We've got a bit of time to ask Carolina some questions, and I can see hands going up already. Can you just wait till the roving microphone gets to you and just briefly introduce yourself? I'm going to go right to the back table first.
Thank you for the wonderful presentation. My name is Fateh, a PhD student here at Imperial under the supervision of Professor Tim. So you talked about the amount spent on balance payments. Pre-pandemic, it was £1 billion, and now it's 5, and then it's projected to be at 8 billion. I want to know what exactly goes into the breakdown of those payments. Does it include the payment for constraints? And if it does, what's the percentage? But if it doesn't, how much of that payment goes into the actual engineering aspects of balancing? Of course, if you can disclose that data, is it just frequency response, up-regulation, down-regulation, or does it include other aspects of the ancillary services like voltage mitigation and synchronization and angular stability, things like that? And secondly, I also want to know, since you have admitted that having data is extremely important, and I agree, what is the ESO doing to make useful data available for academic research? Thank you.
Right, a lot to unpack there, but the beginning of the question was the percentage of constraints. So first of all, everything is included in that dish. So that's all services for that ESO manages. As to the percentage of constraints, there's more that goes into it than just, you know, so you rebalance out. When you have a constraint, you're pretty much breaking the market, right? So you're saying north and south are no longer related. So that means that whatever you are curtailing, usually happens at the border of Scotland and England, actually. So everything north of your B12 or B6 boundaries, which is where we get most of our constraints, you throw away and you re-dispatch the south. So cost there, as of pre-pandemic, is probably around a third of that amount that you're dealing with. So that's why it's one of our top priorities, and it was one of our innovation priorities as well. Going forward, we have published something called a holistic network design plan, which is because there's a lot more wind coming in the UK and a lot of offshore. So one of the things that we're looking at is, like, instead of linking everything to Scotland, can there be, like some sort of different design to the offshore network that will allow to forego pretty much the boundary problem that we have. But yes, it does include everything, voltage, so reactive and so on and so forth. So more detailed explanation of the various components you'll probably find it on the ESO page. We're actually working, I'm pretty sure, with Imperial on understanding what are the components and the growth components on that balancing cost for the future. Because we do believe in theory, we know in theory what impacts it, but you need to be able to forecast it and model it a bit better. And some of these are compounded. So for instance, if you're looking at interconnector trading, the fact that we don't have a plausible model for Europe right now that it can tell you, so what do you expect the interconnector, trade to look like going forward, especially now that you're looking at 20 gigawatts of interconnectors coming, it means that we have no idea of how such a big part of our mix is going to change in the next few years. And what I mean by compounding is like what happened last year, right, with the Ukraine war. So Europe lost gas, right? So there was the biggest gas import in Europe was Russia. And that was gone. So I remember having a conversation internally and everyone being like, oh, that's okay, we buy it from Norway. Yeah, but Norway is Europe, right? So why would they sell it to us? So that's your compounding factor, where gas prices went up for us too. And at the same time, Europe generation was going down. I mean, the import was going down. We became from going from being net importers to net exporters of energy. So that was compounding the problem. Modeling would have helped, right? Knowing that you're not taking them separately. So we were having these conversations separately, and we didn't realize that the things would be connected. So, winter preparedness and stuff like that, readiness is a big deal for us. Second question you asked, and as I said, there's a lot more than what I can sprinkle at you pretty much on this, on our websites, which kind of connects me to the second question, which is data. So we've been really blamed by the fact that we don't really share it. The problem is not that we don't want to. We don't own it, first of all. Data, the way that data works, the laws of data, for what has been explained to me by lawyers, is that essentially, if you generate that data, you own it. So the people who have the assets in the IoTs are the actual owners. ESO is meta in this, right? So we are stewards of that data. We inherit it or we hold it, we're custodians. I still don't understand the difference between custodian and steward, but essentially we hold it for the purposes of system operation and system operation only. So we cannot share everything. The stuff that we do have, we do try to share, but you can imagine the complexity in being able to access it and putting it up in a way that is useful. I struggle with my projects to retrieve data, and I'm internal to ESO. So it's not that we don't want to give it to you, it's like sometimes we just can't.
Okay, well, we'll go to this table here. Thank you.
Yeah, Katrina, it's a fantastic presentation. My question is, you mentioned this 57% of renewable penetration. Do you have some limitation? Can you go up to 100%? And also, what you have experienced, the lowest penetration? And also, for example, one day, do you have the lowest? It's like 5%, 10%? Can give you some indication? So upper limit and also the lowest penetration, and also the hours, how long time they last, the lowest.
Okay, so I can give you only some of those answers. I can assume that the lowest penetration of renewables we had has been 0, right? So it depends on how far away you're looking. There was a time when you had little to no renewables. I think 300 megawatts was the lowest I've heard for the UK, and that might have been about 15 years ago, but I'm not familiar with that kind of historical data. As to how much of it we're looking at, so there's a few limitations. The biggest limitation is inertia that we have right now, right? So when you're saying low carbon or you're saying renewable, it depends on the type of renewable that you're looking at so that you hit that inertia limit. We have to be able to get to a world which is almost 100% renewables. So there's different scenarios that you're forecasting for 50%, 75%, 100%. We could, theoretically, we could have hit 100% renewable more than once in the past 5 years. The reason we don't is because we dope the market. So it gets to a point, though, what it means by doping the market, what I mean by because they will not call it that way, is that when the market would express a fully renewable, setup, we force it to say, hell no. I'm not going to be able to manage this, so I'm going to call in some gas, CCGTs, because I need to bring the inertia level up again. But, considering the studies, and I think it's actually an Imperial project, where we're trying to figure out how much inertia we get. The biggest contributor that we have zero knowledge of is demand, because there's demand contribution of inertia. So once we start understanding that, and the amount that is contributed from nuclear, then we'll have a better idea of how we'll be able to manage that. At the same time, we're also trying to speed up the response of the system, because low inertia just means that things have to happen faster. So we're looking at passive services, meaning not actively dispatched services, but services that can automatically go on. And we're working with, of course, battery suppliers and so on to see if they can match that kind of speed. So it's 192 milliseconds was the quickest battery response we've gotten. So it's kind of starting to get a bit more compatible with inertial responses from thermal generators. So unfortunately, my answer to you is we're not sure yet, but 60% is a pretty high number for us in the UK.
Terrific. The left-hand side of the room, from our point of view, is doing really well. So the third question from the left-hand side, and I'm looking at you guys. So from the front table.
You don't have to ask questions.
Hi, thank you so much for the talk. My background is in theoretical physics. I did masters here about 7 years ago. Last 6 years I've been running a fintech company, and now went back to, I think, science and physics. You talked about how we could have had sustainable future at 60, 70, 80% years ago, and I've done quite a lot of studies, read a lot of the Tony Seba's research, and he talked about Rethink X, where he talked about transformation in food, energy, and the transportation. And it looks like there's a lot of problem, not just in technology deployment, but it's actually the grid system. You talked about the AI could be one of the enablers to predict a lot of the models. I'm actually building a startup right now. Attended one of the lectures last week as well, and there's a company in France, I think it's called Green Yellow, where they have actually managed to build an AI system to help the data centers to reduce the cost drastically. So my question is, you talked about how you help startups, you can engage with you. How am I as a startup, as an entrepreneur, can start with an idea, with prototype, and start actually tackling this grid system? Because it's a huge problem. You can't tackle it on your own. From which angle to tackle first, and what will be the thinking process in order to engage with you guys? Thank you.
So we publish every year the problems of the future, right? So the issues where we're willing to put money in. But one of the things that I've been discussing with some of my colleagues over at DESNES, so it's a new base, is like the government or UKRI or so on and so forth, is that it feels like the one thing missing in the country, so depending on the level your startup is, like if you're looking at a TRL scale, like Eureka got an idea. So you're looking at this presentation, you go home and you start writing, a business plan or something like that. there's a few avenues. You get help. You start with Imperial. Imperial will probably give you your first seeding opportunity. It'll take a percentage, likely if it's like MIT. So you'll start working with them. You apply to a couple of grants, UKRI and whatnot. UKRI will probably tell you, I'll give you 50% if you find industry participation for 50%. You come to your potential customers like myself, like your other network companies, you bring it to the next level. So now you're at TRL 4 or 5. You've got a little prototype or a little program that proves that this works and so on. So you just need to get a bit more scale into it so that you can bring the costs down and move away from cup of noodles into an actual lunch at that point. So there's funding coming up again, other parts of Ofgem or the government that will bring you a bit more scale, they will bring other industry in it. And if you go online, you'll find them. There's competition on flexibility platforms and everything constantly coming out. So if the issue is current, you'll have money. The problem we'll get when you're at TRL 9 and you're done and you're no longer seen as someone who needs help because you're mature enough. That's where I'm trying to work with the government, because it feels to me that what we need is not really more equity. We just need to create an equal kind of playing field where essentially I'm trying to create a sub-market of participants. Because if you go out there and you're competing against your Kraken or your Octopus, they're incumbents, they'll kill you, right? So the only way for you to actually make it is if you have some sort of support. So if they charge, say, 100, I'll give you an example with renewable generation or batteries, right? So why would a brand new battery startup not be successful in the UK? Because it's a startup, right? So for every megawatt hour, they'll charge me 1,000 because they have to pay 6 years of development, plus they've got investors and VCs behind them that are asking for their money back and their investment back. And meanwhile, you got a coal plant or gas plant who've been on it for 20 years, and they're gonna charge me 100. The way things are today, Ofgem doesn't allow me to pick the storage one, because they don't care about the fact that you're developing technology, new technology or anything. They want it to be at the lowest possible cost for consumers. That's actually part of my job. But I'm trying to create a kiddie pool or a sandbox where only renewable, or not renewable, where only startups or new technologies can compete. Because I'm still want to create a market environment. You need to learn from the market. You need to build bones. And to do that, you need to compete. So this is called Project Reveal. It's not here yet. And the biggest part of Project Reveal is trying to create a dispensation from Ofgem for me to become non-agnostic technologically. So where I can pick and choose who participates, the size of them, and for what technologies. But in short, there's many opportunities, but you'll come find me when you're mature enough. Start from seeing what the problem is, understand the problem, see what the contribution you can bring to it is, do some good benchmarking, because there's a lot of ideas out there and a lot of this. But if the idea is good, you're going to be flooded. There's a lot of VCs out there that are coming to me and asking me, where should we invest? Because there's really a lot needed in this space.
Okay. Well, we've kept Carolina talking for best part of an hour. I think we might squeeze one question in, if there is one.
I don't think so.
Okay, Erwin.
I do not remember a single equation from electrical engineering, so.
Oh, it's a good one that this one is a high-level one then.
Okay.
Hi, Erwin Frank Schultz from IBM. So the question is on how can you see, or how do you see your priorities change as you move to an FSO? And I'm thinking specifically about opportunities between integrating electricity and gas control.
So the way that we reprioritize every year is we do extensive consultations, internally and externally. So I ask my colleagues, subject matter experts, then I go out and we reach out to all of our partners. So industry, generators, aggregators, and all our stakeholders and stuff. And everyone gives us an opinion as to what should be the theme of the future. We also look at how much we're spending in each one of these areas. So one of the things about priorities is when something drops out of our priority list, it's not that I don't care about it anymore. It's just that I've got enough money put in that. Let's wait until it grows. and then we look at it again. There's no point in me keep throwing money at it. So an example for this is system restoration, Black Start. We got this huge project. It's one of our top priorities. I've got a single huge project that I'm working on with the Scots, Spen, and a few other partners that are looking at whether or not we can use batteries and renewables to restart the system in the event of a blackout, so black starting the system. It's a £30 million project. That's huge, right? So I kind of let it grow. Let's see what this project tells us before I reinvest. So that's why it kind of dropped out of my priorities. We're still working on it, but it's going forward. Whole system has been in our priority list and has been climbing the ranks slowly as we became more and more involved in the whole FSO conversation. The biggest things that I've seen, and especially coming out of some of the latest publications and, more important tables than the one I sit in, essentially, they're discussing the ability of a single company to cross-optimize across different vectors and sectors. So whole system means, number one, is the type of modeling that you do, which as you decrease the number of boundaries on the one direction, because now you're looking at, for example, if you have constraints going up before, today we're just saying, can you build more lines? Can you, redirect it? Can you build a different network somewhere else? Can you build wind in the south? But what if I start thinking hydrogen? So what if I get a hydrogen, pipe connecting Scotland to the UK? Can I convert electricity into hydrogen and bring it north and bring it south? And then regenerate it using carbon capture to put in some CO2 into the hydrogen, turn into methane again, back in the gas network, into then the CCGTs, regenerated as electricity south of the border. Possibilities are endless. Speaking to one of my Slovenian colleagues, so the head of the ENSOE, which is the European network of TSOs, is the head of innovation for the Slovenian transmission system operator. And they're looking at having chargers, smart chargers, in the different areas of the country. So Slovenia has the demand of London, right? So it's not the exact complexity of the UK, but they're looking at putting chargers in specific areas where they have constraint problems. So it will be cheaper to charge your car in those areas when there's constraints. So that will pretty much attract all the truckers and electric cars there, thus getting rid of the constraint problem all of a sudden because they will take the electricity. So that's what whole system design means. You start working with transport, you start working with other things to try and solve the issue. So on the one hand, increases the complexity of the problem because you're taking away boundary conditions, but on the other hand, it means that there's more solutions that you can look at. And that's one of the reasons why we're looking at generative AI, because I don't think, as brilliant as people in the company are, I don't think they can really take into account all these moving parts at once. That's where you need a, computer brain to help. I hope that kind of addresses.
Perfect. Okay, we're going to take a break for lunch now for an hour. We'll resume at 1:30. Over lunch, there's also the opportunity to look at the posters you saw highlighted a moment ago. I think a few of the posters are yet to go up. We'll address that. But I want to take a moment to really very sincerely thank Carolina. That was absolutely terrific. You talked across and answered questions across a huge range of topics, and it's really stimulating to hear from someone who's leading the stimulation and support of innovation in our industry. So thank you very much indeed.
Thank you.
So please go and enjoy lunch and enjoy the opportunity to talk to friends and colleagues in the audience. Right, welcome back, everyone. Can I ask you to take your seats, please? Thank you. Right, so for this first session after lunch, we're going to launch one of our policy briefing papers. I said at the beginning of the day that what we like to do is take the research outcomes and the models we've got and think about how they answer policy relevant questions, and then have an extended discourse on that in a policy briefing paper. So we have another 3 of these planned for the coming months, but he thought it would be nice to launch one of them in the middle of this conference. You can see the title there. We're going to be discussing how we enable the UK to become the Saudi Arabia of wind, which is a phrase you might remember from a political speech some while ago, and subtitled The Cost of Green Hydrogen from Offshore Wind. So what we'll be doing is hearing from one of the co-authors of the paper. Then I have 3 panelists who are going to, in the first instance, give brief reaction to that, and then we'll open up to questions from you, and we'll see where that discussion takes us. I think there's plenty of issues will be raised and plenty of directions this conversation can go, and I'm very much looking forward to that. So a couple of quick introductions then. The co-author who's going to present is Dr. Malte Jensen. He's a lecturer in sustainability in the Science Policy Research Unit, SPRU, at the Business School of the University of Sussex. So why have we invited our colleague from Sussex? Because Malte spent a number of years working on the IDLES programs in RA, and he's not the only one in the room, but one of the people we're delighted to have seen take the next step in their career. So he's returning to us to give this presentation. And our panelists, I'll take them in the order from, sorry, Malte is the gentleman sitting closest to me. After him is Wei He, and she's principal engineer at Equinor in Norway, where she's worked for 25 years. Very pleased that Wei has taken the trouble to join us today, and Wei has been one of the drivers of Equinor's support for the IDLES program. Sat next to her is Abigail Dombe. She's an energy and sustainability engineer at Net Zero Associates and is chair of Hydrogen Sussex. And finally, Niva Meert-Vils is a senior advisor to KEA Partners and is an innovation consultant specializing in hydrogen technology. So we have an extremely well qualified panel to respond to the briefing paper, and that's what we'll do. We'll hear now from Malte. The floor's yours.
Thank you very much, Tim, and thank you very much, Catherine, as well. I know I've probably one of the few IDLES graduates here, but I feel like I'm coming back to my IDLES families, and that is a big testament to the both of you who have been running the program and giving the opportunities that I've been given here. But without further ado, I will talk a little bit about what it costs to make green hydrogen in the UK waters, and you can see in the background here, this is a collaboration between now me being at the University of Sussex, but mostly led by Imperial College, between Ian Staffel, Ola Sula sitting over there, and Luke. Both of them are the experts with detailed questions that I will have to lean on heavily in this case. But while we're doing this, we'll talk about a bit hydrogen a little bit. So when we talk about hydrogen, I think this is the picture if we put the whole room together. This is, the Germans in the room are smiling because I know what I'm referring to, right? This is the German mystical creature of the egg-laying wool milk pig. And if you were a farmer, this is the thing that you want, right? Like it does everything. This is the all singing and dancing, I think is the English expression to that. And this makes the discussion around hydrogen very often very complicated. So if we strip this back a little bit, we need to separate this out. And a bit more of a technical depiction of that. I mean, this and this is technically the same, right? I mean, if you look at this, obviously. This is a slide that I've actually stolen from Arab, credited below, where they've sort of spelled out all the things that there are. You've got the sort of green production side of hydrogen in the top left, and you've got the sort of fossil-based production in the bottom left, and distribution and the different use applications. And when we talk hydrogen, some of us look at how to use the stuff, some of us use how to transport it, and some of us thinking about how to produce it. And exactly today we'll be looking at about that tiny bit on the slide there, where we look at how to make hydrogen from offshore wind electrolysis and what the cost of that would be. And the reason for that is obviously we're not the first ones thinking about this, but this is in a context where you get a lot of news headlines. So like DNV has done work on this, and then there's targets of let's reach 2 euros per kilogram by 2030. And sort of, Bloomberg is reporting on that, and they all have different studies. And the idea of this briefing paper that we're launching today is to give you a little bit more insight on what we're thinking, what the steps are to achieve certain costs, and how to get there, and to have a very, hopefully, robust discussion about, where we might actually have to tweak those dials to get to those points. But first of all, you asked me why offshore wind? Why do I focus on offshore wind? I mean, it's a magnificent technology. If you look at sort of some London landmarks here, they're truly drawn to scale. London Eye, the Shard, and Tower Bridge. Hands up, how high does the audience think are modern wind turbines that we put out in the North Sea right now? Like, is it 200 meter, 100 meter, 300 meters? Tip height, blade tip height. I know it's engineer, so you need to be specified very clearly. Any ideas? Who says more than 100? Hands up. More than 200? Yeah? More than 300? Some people know. All right, I'll draw the picture next to that. So when you put a modern 15 megawatt wind turbine next to it, you get almost like 265 meter tip height, which is almost the height of the Shard. And we're going to build hundreds of that in the North Sea. So like, as I said, 15 megawatts capacity. Blades are 110 meters long. I think that's longer than the football pitch, although the size apparently varies on that one. It can power 17,000 households, and so on and so forth. So like, we're building hundreds of those just for single wind farms out there, and doing many of those. And the reason why we're doing offshore wind is because it's an incredibly scalable technology, but we've got like large areas of land, something that we quite likely struggle to do with different technologies in the same way. So as a reminder, like, offshore wind is abundant. UK has by far the best wind resources close to consumption centers in anywhere in the world. I mean, they're better wind sites, but you have to go to places where no one's living. So the UK is destined to do that. The energy you get from 1 gigawatt of offshore wind, you would have to do roughly 2 gigawatts of onshore wind, and you need about 5 gigawatts of solar to get the same energy amount annually. And this is one of the reasons why we think offshore wind pairs well with hydrogen production, because it increases the utilization rate of the costly electrolyzers. And you can map this out, obviously, on a map. So this is the UK capacity factors. If you were to put a wind turbine anywhere in the UK, you can see onshore is a bit less and offshore is a bit more. So onshore you get like 20, 30, 35% in good sites. But with offshore wind, you can get 60, 65%. So like, it depends on where you are and the wind speeds and the average wind speeds and how stormy it is and how often they're being curtailed, but so on and so forth. We're being presented here with probably the largest decarbonisation tool that the UK has in their arsenal. I'm not saying the others are not valid, and there's a good discussion to be had within the IDLES program as well as with a bigger community. But it also goes towards the UK's target of 10 gigawatts of hydrogen production by 2030. Although reading the news this morning, I know Prime Minister Rishi Sunak is thinking about scaling back some of those ambitions. We can talk about this as well. The second reason why we're doing offshore wind is because it's presumably cheap. And I probably put this in here because it's plugging 2 papers that were sort of key output from the IDLES program on what I've been working on. So on the left side, you look at prices in different jurisdictions. So there's a global picture on how the bid prices have come down from offshore wind globally. So there's a trend obviously going towards more than 50 euros per megawatt hour mark, but you also see the zero bids down there, that's predominantly Germany and the Netherlands because their system is working differently. And on the right-hand side, you see sort of more the cost representation behind those bids, where you go, we kind of reached sort of the 50 euros per megawatt hour mark. So keep that in mind. So it's a relatively cheap technology. It's definitely cheaper than anything you could build or operate right now under the current fossil fuel prices, even though, I mean, you probably read the news that the UK CFD auction hasn't attracted any bidders this time round because the price cap was at 44. Even if you consider those things, we can consider offshore wind a cheap and mature technology in this context. So why don't we all go up and board the hype train? And you can see that's been done actually for COP, I think 26 by now, on track to net zero. I think they scrapped the train now because they've ripped out the electrolyzers again, which is a shame because I really like the train. But to come back to the more like sciencey bit of it, and I promise you I'm not going too heavy on the equations because I, actively dislike equations in presentations. But a good energy modeler, what does a good energy modeler do? I mean, obviously we're building a model. This is a sort of a really rough representation of what we're doing. We have a wind turbine that we can stick anywhere in the North Sea. And then we need to do something to get the water in, desalination plant, electrolysis, compression. And you can imagine there's a lot of technical parts of that they need to evaluate. You need a platform where you put the electrolyzer on, and so on and so forth. But ultimately, all of these, what the economist part of my brain says, all of these are costs, right? I mean, all of these things contribute to how much does it cost to build, to produce hydrogen. And the way we typically express this sort of in the energy world here is levelized cost of electricity, and this is its equivalent brother, the levelized cost of hydrogen, LCOH. And because I really dislike equations in here, I will spell this out for you a little bit to know what it means. So at the top you have CapEx and OpEx, or the capital expenditure, the operating expenditure, which is data that you have as a developer. So you know how much it costs to buy 1 megawatt of wind turbine. So there's index prices out there. You can, like go to the producer and say, like, how much are you going to sell this for? So the idea of that is you're adding up all those costs, and then you sort of dividing them by how much you produce. So at the bottom, so the production of hydrogen, T is the hydrogen production, comes from the wind production, plus some sort of conversion process that you have. So the electrolysis, how much efficiency hit do you take from that, and so on and so forth. And then last but not least, is the discount rate. And I think this is typically what energy modelers sort of disregard. They take a discount rate of whatever they find in resources, either 5 or 7%. I think that's what people are putting in. But the idea of that is the time value of money. How much does it cost you to get money to build those things? When you take it, really does matter significantly. And I think we'll probably find this in discussion later as well, at least with the way I had already preluded our standoff on, I've got this cost, you got those costs. It's worth thinking about those discount rates. And I think that's maybe that's one learning to take away. It's worth looking at those discount costs much more closely, because of cost of finance is going up with inflation, and that means especially capex intensive technologies, so like have no fuel costs but lots of upfront costs, will be harder hit from that than, for example, technologies like gas turbines or coal power plants. So that's worth considering if we're doing this kind of modeling. What the Bank of England does really does matter. Breaking down the methodology a little bit further, in our concrete example here, we've got renewables data, weather data that goes in. We make, wind farm output. We calculate the wind farm output from a chosen turbine design at a chosen location with a chosen depth that then informs the capex parameters. So like how much does it cost? So if we go too far out, we can't use AC cables anymore, but we need to use DC cables. If we go into a location that is too deep, then you need to use floating foundations rather than fixed foundations, and then so on and so forth. There's a lot of location-dependent variables that determine how much you spend up front to build an asset out there at sea. You make certain assumptions on equipment capacities and efficiencies. So, I mean, how many stacks do you need in electrolyzer? How many units do you need per gigawatt? So they don't come in a gigawatt size box, but they come usually in a, I don't know, 2, 3, or 5 megawatt unit, and then you increment them until you get the capacity. And then you make those final financial assumptions that I've talked about, and you wrangle them all together, and you essentially, based on location, you map out the levelized cost of hydrogen in this case. We've done that using, I say we, I mean that's been Luke in this case, done this using a Python-based model that we've written from scratch. And so we just, have the ability to change those assumptions relatively quickly. And the idea of that is to do this eventually as an online model for you guys to use, where you can put in your own assumptions. So like if you think the discount rate we've put in, you disagree with that, you put your own discount rate in based on what you think is right. If you want to do this for 2030, then you might want to, put different cost assumptions in there. That's up to you. So that's the sort of the next step from that. But when we look again, our old friend LCOH, and I've given you enough of that, I want to show you the data now. You can see the capacity cost, how it varies by location. So you can see the closer you are to shore, the cheaper your capex is, your capital expenditure. So if you go further out, it gets more expensive by those factors of like distance and depth. And then you can see, obviously, there's some regions where being close to the Orkneys or Shetlands has a cost advantage because you're relatively close to shore, which means you can use an AC connection, presumably reducing your costs. But also you're in relatively shallow water, allowing you to use fixed bottom turbines rather than floating turbines. And the other one I think that I would like to point out is the hydrogen production that you get. So there's MT, where you can see the further up north you go, and that correlates really, really strongly and really directly with the wind speeds and the capacity factor of your wind turbine. So the further north you go, the better the conditions are. So unfortunately, the best production values you get up north, and then you need to find a way to bring the power down to more, consumption centers, like the southeast of England, for example. And the result of that is the map to the left, which, barring some differences, maps reasonably well with the capacity costs. So the cost of hydrogen correlates relatively highly with the, not capacity, capex, not capacity cost, the capex, the capital cost. But you can also see that, so for example, there's a little bit of a line between Ireland and the UK. I don't know if you can see that on that screen, but that's essentially the difference, not in sort of wind speed or capex, but that's the difference in financing costs. So you can, when you map this out globally, and I'll show you that in a bit, you can see those differences very, very clearly. So moving on, so we take all the UK locations, and essentially what we then built is a UK hydrogen supply curve. So very important to note, this is based on the assumption that we've put in. So we've had a relatively low wind farm cost. We've taken the last year's UK CFD round as inspiration, and we've got relatively low finance costs as well. So like you get relatively low costs. And then you essentially put all locations together, and then say, like, this is the price that you're going to get for those assets. That's production only. There's no transport in there. It's like, it doesn't say how you get it to the place where you need it to be, and that is, with hydrogen, a considerable technological and financial effort. But if you then look at the global hydrogen demand, the UK could potentially supply what is being used right now in hydrogen demand. Not necessarily at the cost that it needs to be, which is still competing with just sort of natural gas prices, which I've put in here just because, before 2021 seems to have been September 2021 seems to have been a stable time for gas prices, at least in relative terms to now. So the gas prices obviously influence competitiveness here. But there is a case to be made that there is an abundant resource which could be tapped into for supplying some of the hydrogen applications in the world, most likely in Europe. And if you think about this from a logical point of view, so those hydrogen applications are mostly chemical feedstocks, and a lot of that goes into fertilizers. The things that we're talking here in the energy world will be a multitude of that to come if we decarbonize transport, heat, and what was the last one? Industry, that's the one from that. Without further ado, I'll give you a snapshot of the report that we're just launching. I did check the QR code, it's working. I'll put this on in the end one more time to download. I'm sure the IDLES team will disseminate this accordingly as well. I don't know, I keep looking at you, Mirabel. But yeah, please have a read, give us feedback. We're really happy to hear. And this is, this is our findings on this one. I've got 2 minutes left according to my clock, so I would like to give you a little bit of a global outlook and what we're thinking here. I'm glad this is coming out nice and big. So 2 things we've done is we mapped this global, with this LCOH, this levelized cost of hydrogen on a global scale with some restrictions on how far offshore you want to go. Obviously, it's not reasonable to go beyond X amount of miles from shore. And you can see if you focus your view on the most southern tip of South America, for example, these are very similar wind resources here. And you've got 3 countries or 3 territorial waters down here, which you see the clear demarcation line between the Falkland Islands and Argentina, for example. Just that's the sheer influence of the interest rate that we're doing. That's got nothing to do with necessarily the capital expenditure or with the resource. That's the finance playing a big part. So I think we're doing a lot of technical modeling and sometimes forgetting about this a little bit. But you can also see that the UK is incredibly well placed in terms of, being the Saudi Arabia of wind, as in access to relatively cheap wind resources to exploit in relatively shallow waters. But surprisingly, you can also see sort of the wind belt of the United States and also like Australia, especially Southwest Australia has an exceptionally wind source that can be exploited. We've also done this for solar. Another time, and maybe I keep banging on about the finance cost again too much, but you can see really good low values for Southern Europe, especially western part of the United States, but also China. And then surprisingly, you have relatively high values for Saharan Africa and other parts of the world. Yet again, when you put in the interest rates into those equations, it really does make a difference that potentially, like north of England doesn't, in terms of cost, doesn't fare too poorly against other parts of the world who just are lacking the financial infrastructure to provide funds reasonably cheaply. And I promise that's the last slide. And the last but not least, and this is very much work in progress, is we're looking at where in the world would you be cheaper using wind to produce your hydrogen or solar to produce your hydrogen. And this is just a binary map. This is like either blue or either yellow. I mean, there's probably different 50 shades of blue and 50 shades of yellow in there, which you can sort of articulate. But there are some very interesting sort of Western United States seems to be cheaper, and then parts of Asia. And please disregard anything in sort of the northern elevations, because the model says the colder you get, the more efficient the solar panel gets, which is obviously, as we know, not necessarily true. The opposite is true. The hotter it gets, the less efficient it gets. But so like anything with sort of in the area where people live, this is relevant. But as I said, it's very much work in progress. I'll put the paper QR code on there one more time. And I think I'm really looking forward to the discussion. Thank you.
Of course we're looking forward to the discussion. We enjoy those things. So thank you very much. And yeah, in the post-event email that goes out, we'll put a link if you're unable to grab that QR code right now. So what we're going to do is work through my three panelists here and to get some reactions to the briefing paper and to Malte's comments, and then we'll pass back to Malte for the reaction, and then we'll do some Q&A. So, Wei, I'm going to ask you to go first. Would you like to give us your thoughts, please, in a few minutes?
Yeah, my name is Wei. I work at Equinor, as Professor Tim Grant have introduced. And first, thank you very much for inviting me to review the paper and also serving at the panel. And I have 3 points. The first point, I think, as you mentioned in your paper, and this offshore wind, it has a fantastic development the last 10 years. And the next 10 years, it will be very crucial. You also mentioned, and this offshore wind will go far offshore, and also the metocean condition will be more harsh, more challenging. So, and also from the investment, and the next, like a future offshore wind farm, will not depend on the government support anymore, have to be full commercialization. And so that's really require and very much efforts. And the second is this power, what you produce cannot be like 100% absorbed by the electric grid. You really have to competing. So at Equinor, we are very very passionate for this offshore wind, and of course oil and gas is still our main sector, and we have applied our oil and gas, offshore oil and gas experience for developing offshore wind sector. So I think we already contribute very much, and for the developing the offshore wind farms. But for further go for the next 10 years, and it's very much like challenges. We prepared, for example, 10 innovations for our next generation of offshore wind farms. And hydrogen production is one of the 10 innovations which Equinor and we are promoting and we are supporting and we are developing. And the second point is hydrogen, as Matt has mentioned. It's a fantastic alternative, very promising, and matching the development, further development for the offshore wind. Because offshore wind, and now it's the cost have to reduce, and also this power balance and the energy storage, and the hydrogen will provide the new opportunity. The third point, as you mentioned, and the cost, it's very demanding. And for the commercializing special offshore hydrogen production, I think there are at least 3 challenges. The first challenge is hydrogen production. It's more like a chemical sector. And they needed to integrate with this green power generation. So it's like a green power generation, and you mentioned this, it's like every second the power is variation. And also days and weeks and months. And you might have 2 days without power generation. You might have 1 month without surplus power generation from one offshore wind farm. And so the balance from different sectors, that's really, really a new challenge. And the second challenge is offshore operation conditions. I don't know how many of you have been traveled offshore, and I worked 10 years offshore, and by helicopter go to work. So the cost offshore facility is not like 10, 20% higher. And at Equinor, and for our oil and gas sector, we calculate almost 10 times higher cost offshore compared to onshore. And so we see working for offshore, you see it's like a blue growth, very few players for the offshore sectors. And offshore is basically 3 high, very harsh environment. You need a high investment cost and a high technology and high risks. And so how much time do I have?
Well, if you could just conclude that remark, that would be good.
So I just want, so I mentioned this at least 3 points. So it's the third point is the supply chain. And for this hydrogen production, and you move from onshore to offshore, and you need a whole supply chain. So this is also very demanding. And so I think this paper will kick off this offshore hydrogen production. And so we're looking forward for more discussions and further development. Thank you.
Thank you, Wei. I can see you taking notes, Malte, so I think you're happy for me to run through the panel and then come back to you. Terrific, thank you. Abigail, please.
Thank you. I mean, I thought that was a really interesting paper, Martin, so, and a great presentation. I don't have quite as many comments as Wei. Hopefully you'll be relieved to hear. One thing that in the presentation you were talking about, you were referring back to the prices, comparing the price of green hydrogen with the price of grey hydrogen prior to the invasion of Ukraine. And I was wondering what the impacts or what the comparison is now with increased price of grey hydrogen, because we're expecting for energy prices to remain higher than they were previously for most of this decade, although not as high as they were necessarily this time last year. I'm not going to comment on electrolyser efficiency because I'm sure Nivo is more than able to cover that, certainly more capable than I am. But I was thinking actually something that Wei mentioned about the supply chain is that there's a huge crossover with ports. I mean, ports obviously are often, they can be the supply point for and the land base for offshore wind infrastructure anyway, for the building of offshore wind and the maintenance. But they're also they're natural hydrogen off-takers. Longer term, hydrogen is going to be absolutely invaluable for decarbonising the maritime sector. But predominantly most ports have significant HGV, heavy vehicles passing through the ports, which again, HGVs lend themselves, or hydrogen lend themselves to HGV use, and for port vehicles themselves, hydrogen can certainly lend itself to port cranes and the like. And I mean, in my case, I'm coming from Sussex. We've got plans for hydrogen production facility at Shoreham Port, and they have a power station next door, and they're looking at the potential for using, for mixing some of the hydrogen in with a gas grid and using it for dispatchable power. So that could be a potential as well. Yeah, I mean, the alternative is kind of, as we heard from Carolina earlier, is there's this huge impasse basically at the border between England and Scotland, where we just don't have the grid infrastructure to manage the vast amounts of wind power, wind generation that we're getting in Scotland. And we do need potentially more interconnectors, not between the UK and abroad, but between Scotland and England. And we need that power, as we said, the power that's generated in Scotland down in the southeast of England, supplying the southeast, and that, you know, might be a more immediate solution. Well, I say immediate because we all know that there's huge logjam in the planning in the UK. But that's my comments for now. Thank you.
Thank you very much. Nivo.
Yeah, so thank you to the panelists for your input. Thank you to Malte for this great study. I always find it fun when somebody goes out and tries to quantify whatever Boris Johnson said. So thank you for this contribution. I guess looking at the figures that you presented, the thing that strikes me is, despite the amazing cost reductions in offshore wind technology, we're still looking at an levelized cost of hydrogen between 2 to 3 pounds per kilogram, which is what, $3.5 per kilogram, $2.5, which is quite expensive. It's still twice as much as the cost of gray hydrogen from fossil fuels from before the invasion of Ukraine. Now, we can debate whether there has been a structural shift in the price of natural gas. I think there has, but by and large, gas has returned from its recent highs, and the cost of fossil hydrogen is maybe at most $0.50 per kilo more than it was, so maybe $1.50 per kilo. So still, newest technology, despite amazing cost reductions in offshore wind, we're still looking at 2 to 3 times more expensive hydrogen in the UK. And it leads me to question whether the Saudi Arabia of wind can actually compete with the actual Saudi Arabia. I think one of you showed 2 cool charts, which showed the cost of solar hydrogen and which showed the cost of wind hydrogen. And I spotted that actually Saudi Arabia was doing quite well in both. So I'd have loved to see how Saudi Arabia, how the cost of hydrogen works out in Saudi Arabia. And I think that holds the key to answering the question, can UK be the Saudi Arabia of wind? But there was another thing that I wanted to touch upon, which is offshore wind the best partner for hydrogen? And the answer to me isn't clear, because on one hand, you do have high capacity factors, which are beneficial when you have expensive electrolyzers, but over time, the cost of electrolyzers will go down. So that's one consideration. I think you've actually modeled that, though. So I would have loved to see a time series of how the cost of hydrogen evolved. But I think what's really worth also exploring is the dynamic of hybridized hydrogen production models, where you have supply from different power plants. So you'll have a little bit of biomass, which of course we have Drax in the UK. You'll have a little bit maybe of new generation geothermal. You'll have a mix of offshore wind, solar, and maybe even nuclear. And all that adds up and maximizes your capacity factor. And all the while, if you have a source of high temperature heat, for example, geothermal and nuclear, you can situate your electrolyzer next to that and squeeze out an extra 10% in efficiency. So wrapping this up, is offshore wind, I guess the question I'm asking, is offshore wind the best partner for hydrogen? I think it is a good partner, and I think your paper shows that there is potential in there, but I would like to ask you or rather, I would love to see how hybridized models also interact with that. Thank you.
Terrific, thank you. Well, there's a lot to chew over there, Martha. Good luck.
I wasn't about to say, but are people distracted by the flowing seas? Should I stop the video animation? Okay, good. You're thoroughly getting sleep. I'm not dodging your questions. Let me maybe start with is offshore wind the right technology? I think going back to the conception of the study, I think it was driven by scale and speed that you can do rather than by cost and efficiency. So if you were to go for the lowest cost wind resource in the UK, you would go onshore. Those of you who have been following UK policy making the last 10 years, essentially onshore wind is banned in England. So if you were to rely on that, so that was the conception of the study. So I am dodging a question on that one, right? Like I mean, we're sitting, UK is having its third energy revolution. Like first it was coal, then was oil and gas, and now we're seeing wind being deployed. The question of additionality, and that goes to the other panelists as well, like offshore wind has the ability to provide that additionality. The land over in Scotland or England, wherever, to build wind turbines is relatively limited. I hear again and again, oh, this country is already, relatively populated, and it's hard to find a place for wind turbine. And then the logic behind that is offshore. There's a lot of resource there, especially if you go far north into, places where not too many people live. So, yeah, I guess offshore wind is maybe not the right technology, but it's the most likely to be deployed at scale that we need to decarbonize our energy systems by 2050. I think that's the caveated answer. I agree on the still being expensive. Coming from the far end, sorry, way, I'll get at $3.5 per kilogram. And yes, that's right. My answer to that is look at Michael Liebrecht's hydrogen ladder. I think he keeps posting that on LinkedIn. There are certain applications where hydrogen is used better, more thoughtfully, in a more efficient way. And now I've been hooking you in with heating and transport and all of that, but quite likely hydrogen has a value in feedstock applications, maybe some industrial decarbonization, which don't have access to or can't do carbon capture and storage and those kinds of things. So it's really worth evaluating what we're using this hydrogen for, because it is quite expensive. It will have to be subsidized or paid for by someone if we want to make this happen. So it's extracting the maximum value out of that with the right application, I think is, but that is delving into the sort of, demand side and how do we use this stuff. Let's see, the right-hand side of the Arab chart that I've shown you before. And the third notion was the dynamic of hybridized power plants. I do agree with you. I would think that is a second study after that. So obviously we're working on a journal paper here, and we're trying to frame this in a way that is, a clearly defined line, around the system boundary. And once you start mixing different sources, grid electricity, you use heat for potentially high temperature electrolysis as well. I think that's what you're referring to. You're getting in a very difficult discussion around costs versus values. So who pays for the cost, who extracts the value, is a very different discussion than looking at costs for now. But I agree that we should be doing this. And maybe we should be doing another funding round for this to answer this question a little bit more. Then, Abigail, you had a question on comparing green and grey hydrogen, especially I think with the Ukraine crisis was your comment. I've sort of, if the gas price goes up, that didn't happen everywhere in the world in the same way. And the way the European economies have reacted, at least in parts, is shutting down industrial production that relies on natural gas and hydrogen. So some of the production, at least, has been moved overseas. I'm thinking a lot of that has moved into North America, who have access to much cheaper gas. So I think there is a sort of shifting effect globally on where the product is made, because once you've got hydrogen-based fertilizer, ammonia-based fertilizer, that stuff is relatively easy to ship around the world in bulk and has low shipping costs attached to that. There's a crossover in ports, and I agree with that on infrastructure. And we need to think of how do we get hydrogen to the users. And part of that has been, shipping and ammonia, or ammonia and shipping to replace as a drop-in fuel to replace, not necessarily drop-in fuel because you need to change engines still, but as a fuel that can be shipped around relatively easily around the world. And ports take a significant role in that, being that access point. Other parts is, coastal communities. If you think of Teesside, with industrial clusters, I think that is highly relevant on how to tap into those potentials using the hydrogen. And lastly, you mentioned the Scottish-English border, which is anecdotally, you can always tell when you reach Scotland, because you start seeing the first wind turbines when you take the Avanti West Coast up, exactly. And I think that is, there is just the production side, but obviously you need to get the stuff down to either the southeast of England, or you need to build up the demand for industrial applications up to where the wind is. So like we're doing nothing short of rebalancing the entire system around where energy is being produced and where energy is being used. And I feel like I'm hogging the time here, but you deserve an answer as well, Wei. The future of offshore wind is really, really interesting. So like we're facing sort of a massive storm of supply chain issues. The manufacturers allegedly are not making any money on the wind turbine production. So if you see the warnings from Siemens, I think they've just written off 4.5 billion euros on their wind division. Hence why we're not seeing maybe a new generation of wind turbines into the 20 megawatt class. So I am worried, but optimistic for the future. I think this is, we've seen this before. We've seen this in the early 2010s where offshore wind was struggling. I hope this can be overcome. And the second point was not all wind can be absorbed by grid, and that ties back into the additionality. What we're thinking here doing is creating additional wind generation that doesn't take away electricity that otherwise would go into the grid, but that goes directly into hydrogen production. So you're creating that, that energy supply for all the other applications. And the costs are demanding, and I say yes to that. Yeah, because I've seen you try.
Yeah, and I'm conscious we've probably not allocated enough time to this to go to our panel and to yourself, Malta, enough times. But I'm going to open up and ask for some questions from the audience. I've seen one hand in the front here. Can we get, Catherine, we get a roving mic to this table? And then the table behind. So maybe we take both those questions and then we'll run along the panel for responses to those.
My name's Nick James. I asked a question earlier, local resident. You mentioned the cost is high compared to grey hydrogen, but I'd argue that there's another cost. If I get a car to go green, I'm going to go electric and use batteries. I don't want to use hydrogen. 3 reasons, not just the cost of the fuel, it's the cost of the car. It's 5 times the price of an electric car. So transport's nonsense. The other thing in terms of efficiency is the cost of it's indirect. So they've done a comparison. Electric vehicles running on cables like trolley buses are more efficient than battery vehicles, which in turn are more efficient than hydrogen electric vehicles because you're going through a secondary process of making electrolysis before you put the fuel, and then you've got to run a gas piping network for it, which you don't with electric. And the other problem is safety. I think of the Hindenburg. Hydrogen is dangerous. You have to have a bigger container than you do for oil, and I wouldn't want to be crashing a car that's got a hydrogen fuel tank. So there's those 3 issues, and I think we should go down. I'm all for wind. Wind is great. We should store it in battery storage systems and send it through electric wires through the grid and do it that way.
Okay.
My question is, what your thoughts on that are?
Okay, and I want to pick up the second question, and then we'll run along the panel and see what you
Hi, I'm Yusra from London. My question is talking about cost efficiencies and supply chain challenges, particularly for industries and manufacturers. As we have seen in the last couple of months, big companies like Ørsted, Vattenfall have withdrawn from projects, offshore wind projects in the North Sea, and the other one in the US, if I remember correctly, for Ørsted. They have withdrawn before the completion of the projects because they could not manage the continuous rising costs, and thus it caused conflicts with their operating models and supply chains. My question is, what's your take on that? And how do you think we can avoid this scenario in the future? Thank you.
Okay. And I'll take a third question off the table in the front.
Hello, this is Bülent Mehmetli from New Renew Limited, and I'm also representing Institute of Power Engineers. So we know the problems. There's huge supply chain issues, cost issues, but they were known. But in the failure in the auction round 5, and what does it take exactly to take big players like Equinor or Vattenfall or RWE to get back to the offshore wind? So is there a bank rate that you guys are targeting for? As I see, the financing seems to be the biggest problem. So would you be waiting for 2 to 3 years to come back to the offshore wind?
Okay, so there's lots of different issues in there around supply chain and financing and safety and all sorts of things. So what I'm going to do is run down the panel and just bite off whichever bit of that you fancy. Don't feel obliged, all of you, to answer everything, because we won't have the time. And why don't I just run down this way? You for me.
Sure. So I'll take the question from the gentleman over here. Of course, hydrogen is less efficient, and therefore battery electric vehicles will probably win. Heat pumps and residential heating are probably a better option, of course. But then there's the big question of the UK industry and the UK refineries. And when you're in a position when you've got so much of your industry reliant on hydrogen, what is it that you do? Do you just let go of this industry? Do you just let go of this industry, or do you try to switch it to a fuel that's green and that's compliant with your net zero targets? And in this case, there is no other option. You cannot just, you can replace a steam cracker with an electric cracker, but guess what? At the end of the day, you're still gonna need hydrogen. So your only option is to green it. Or if you decide, okay, I cannot afford to green it, you end up importing molecules from somebody who can do it cheaper, maybe can do it cheaper, let's say Saudi Arabia, actually, in this case. So this is a strategic question about whether you want to keep this industry and the entire ecosystem that surrounds it, because remember, refineries don't just exist in a vacuum. Their entire ecosystem is dependent on the outputs of these refineries. And this is an industrial policy question.
Thank you.
And just to add to that, it's not just oil refineries. We do still have some steel production, and that's going to be dependent on hydrogen for the reduction of steel. So of iron reduction. Sorry, that's going to be dependent on hydrogen. We do make some fertilizer that's going to be dependent on hydrogen. So there are areas of industry where hydrogen is absolutely essential and will be essential. There's also high temperature industry, which will have to make the decision whether it goes down to using electric burners for their processes or revamps their entire process to work out how it can achieve their final product without natural gas, or whether it goes down and uses hydrogen for that. I was working on as it was then, a BEIS-funded industrial fuel switching project last year, and I'm continuing to work on one this year, which is looking at replacing natural gas with hydrogen. So we do need hydrogen in all sorts of areas across industry. Just very quickly to talk about transport. I was in a hydrogen fuel cell bus just yesterday, operated by a Metro bus just around the Crawley-Gatwick area. As Nivo Mir said, direct electrification is always the better solution. If we can achieve direct electrification, whether it's a battery or a pantograph, yes, it's far better, it's far more efficient. However, there may be electrical constraints, so constraints in the grid, again, at point of use rather than point of generation. There may be demands of timetabling or vehicle demands or constraints in the depot, or all sorts of constraints that mean that right now, if the fleet is going to decarbonise, then hydrogen is the only solution for it right now. Maybe 5-10 years, that's going to be direct electrification. But I think, we always have to look at the different use cases, and if direct electrification and other use cases if direct electrification is possible, then that's what we do. If it's not, then hydrogen will need to be used, and yes, it is flammable, it is explosive, but then so is natural gas, and we've got, it yes, it has different properties, but we're all used to using natural gas in our homes. Not that I'm saying that you should use hydrogen is a good source for domestic heating, because it's not, but we are all relaxed using natural gas. And we can, I think in industry, we can switch to using hydrogen, and I think in transport, we can switch to using hydrogen where it's required.
Well, okay, I'm however going to keep moving. We've got a coffee break. We can pick up some of that detail, and please do. Wei, there's several questions actually about your competitors withdrawing from markets and how that might play out in future.
Yes, I think this gentleman asked for this offshore wind farm and hydrogen. Should, when offshore wind farm have many challenges, difficulties, should we wait? Or we should utilize hydrogen and production as some kind of synergy, and to create the next generation of offshore wind farm to meet the future challenges and overcome all the cost barriers. And so I think there is many challenges, as I mentioned, and this also in your paper has mentioned. And commercializing of hydrogen, it's a long process. And also from onshore move to offshore, many challenges. And but they do have some synergies with offshore wind farms. So these two pair, so they might help each other, create some new opportunities. So though they also have many new risks. And as Equinor, and we also have real from the strategy department. And Dog Bank, and which Equinor is the developer, one of the developer. So we are still going on. So they are installation, and as you showed this one, and the 15 megawatt wind turbine has been in the installation stage. And it's quite important, and I think they are all very new and emerging technology, and it's like you need learning by doing. And also this, all this hydrogen production, both green hydrogen production onshore, offshore. So it's, so in my opinion, still we should not stop. We should do more demonstration projects and different sectors, and should cooperate, and also closing the gaps and between the research and industry demands. So I feel there is a large gaps, and between the all the research results, what you are busy, and how to accelerate the commercialization, and the results and the tools and the models, how can push the project go, no-go decisions. So there are many research papers and works, but when we have a project, we really want to make a go, no-go decisions. So then we feel we are very shortage of all the tools. So I think the gaps is very important. And also this gentleman mentioned this safety. Safety, it's highest priority for all the developers. And so safety, it can be like a sure stop for many projects. Yes, thank you.
Walter, last word to you.
Yeah, not sure I can add much to that, but maybe picking up a little bit of the value side, right? Like we're not pitching hydrogen as a replacement for battery-driven applications, but it creates a value on a system level, which is its storability in bulk. And I think the IDLES program had the output on the Dunkelflaute as well. I think that was Marco Nadi's paper, good paper, which is sort of, the wind lull that once in a decade, once in 50 years kind of events where you just don't have enough wind and solar to keep you going, where it's very cold. And hydrogen has the potential to be, used in gas turbines to be dispatched for that. And I think this is something that we ought to consider when we're doing this. There's a strategic value in that. I don't know what value to put onto that yet.
Great. Well, thank you very much. And I said a moment ago, please follow up with some questions at the refreshment break. Sometimes, that's said as a deflection. I'm saying it because we have assembled here some tremendous expertise across our three panelists and the team of people, and Malte representing the team who wrote the paper with a tremendous range of expertise. And I feel, sadly, we slightly underused you. So please make up for our poor organisation on that and ask some questions in the break. But I think I was really pleased with that debate. I think what we're seeing about hydrogen is a maturing. It was the solution for everything and then the solution for nothing. And I think we're gradually getting there with the contributions that you good people have made in narrowing the debate to exactly where does hydrogen play its role in the system and where does it bring value and what's it going to cost. So I think we've marched that forward a bit, and for that I thank you very much. Okay, thanks guys. So we're going to move on, and I'm going to introduce my colleague Wolfram, who's going to chair the next session. Wolfram Reisman.
No, I just need to give back the... There's a whole argument of value to be had. Thanks. Thank you very much. I'll take the glass. Okay.
Great. Hello everyone, welcome also from my side. So our next speaker is going to be Marco Aunedi, who's an advanced research fellow at our Department of Electrical and Electronic Engineering. And Marco's research interests are varied. He's interested in low carbon energy systems, in energy storage, demand side flexibility, as well as the use of electric vehicles. And today Marco will be talking about system-driven design of flexible nuclear power plant configurations with thermal storage. Just like the other talks, what we'll do is Marco will present for about 15 minutes and we keep the questions until the end, if that's okay. Great. Thank you, Marco. I think I will just hand this over.
Good afternoon, everyone. My name is Marco. I'm going to be talking to you about a piece of work we've done as part of IDLES. It's also a good representative of interdisciplinary work because it's been done in collaboration between two teams, one which has an energy system expertise and the other one which has more energy technology expertise. So the overall objective was to study if you could make a nuclear plant more flexible by adding some thermal storage, what would be the best way to do it from the system perspective? And we also wanted to explore, do the system features, system characteristics affect the cost-efficient choices of how you should configure your flexible nuclear plant? This is, as I said, been a collaborative work in which my colleagues Abdullah, Marco, Christos, and Goran have been included, and I'll also mention some of the publications we've done as part of that. So to give you a bit of a background, obviously, we know that the expansion of variable renewables it will be one of the main ways of decarbonizing energy supply. And we also know that these renewables will require quite a lot of flexibility of various sorts, whether that would be energy storage, demand-side flexibility, more transmission and interconnection capacity, and so on. On the other hand, what we've also seen recently is the reduction in cost in variable renewables. And that reduction in cost has made them significantly cheaper in most cases than conventional nuclear energy. So nuclear plants, although they can also provide fairly reliable and non-intermittent supply of zero carbon electricity, it's become difficult for them to compete on cost basis with variable renewables. However, we do know that renewables will require additional flexibility. We also know that nuclear plants are probably not the best, at least not in the standard, let's say, variant, are not the best way of providing flexibility to the system. So in theory, you could ramp nuclear plants up and down, and you could modulate the output. But because of the economy of how you build nuclear, and that is that you invest a lot, it's very capital-intensive technology. You need to invest a lot to build the capacity, and then it's fairly cheap to run it once you have it in place. So with that sort of economic setup, you would ideally like to run that plant at full output for as long as you can. So you wouldn't want to be flexing it up and down. So the question is, could we do something to make that plant more flexible without sacrificing the positive economics, so the cheap fuel costs? And an obvious idea would be to include something in the thermodynamic process in the nuclear plant, which would be a high temperature thermal energy storage. So that would allow you to still continuously run the reactor and the steam generator to generate the heat that you would otherwise directly use to produce electricity in the turbines. But instead of using it as it comes, you could store some of it in thermal storage and then use it later depending on the circumstances in your system. And another interesting aspect is that this is something that you don't necessarily have to do just when you build new nuclear plants. You could also retrofit that to existing nuclear plants. A lot of them will have to go through retrofits anyway, so that's something that might be an interesting proposition. So we wanted to look at how does this compare from the system point of view, and what are the costs and benefits of different options. So there's been quite a bit of work done on studying different nuclear configurations. We've played with that a little bit, so taking some kind of off-the-shelf configurations with fixed parameters. But what we wanted to do here is to see, does our system modeling, can it tell us something about what that nuclear configuration should look like? And does that vary depending on which system we are putting this flexible nuclear in? So to do that, we needed to obviously develop and enhance our existing energy system models to directly consider flexible nuclear technologies and all the components that involves. And we also had to have reasonably good cost estimates for these additional nuclear components, so for the thermal energy storage and the extra generation, which I'll talk about on the next slide. And then finally, as I said, we wanted to see how different system features would affect those choices. So what do we mean by flexible nuclear configuration? The picture is slightly too busy, but if you just, I'll just take you through the main components. So the bottom half, you can't really see that. So the bottom half of this picture is your standard classic nuclear plant. So on the left, you've got the reactor, and as an example, we use the EPR, or European Pressurized Reactor, which is then obviously where the nuclear reaction takes place, and then you heat water and turn it into steam. So that's happening in the steam generator. That steam is then taken through a set of turbines, high pressure turbine, low pressure turbines. There are also some additional components that improve the thermodynamic efficiency of the process, but effectively you turn the energy from that steam into electricity by spinning the generator, and then the whole thing gets pumped, condensed, pumped back into the steam generator, and the whole cycle repeats itself. So that's what's called the primary steam Rankine cycle. So that's how your standard nuclear plant would operate. A nuclear plant with more flexibility would then start having some additional components as shown here at the top. So I can't get any pointer to work, so you'll just have to take my word for it. So the two sets of drums that are labeled PCM, that's short for phase change material, represent the thermal energy storage. Now the parameters of that thermal storage have to be chosen fairly carefully, because that's very sensitive to the temperatures and the pressure of steam you've got. And then if you charge those thermal storage tanks from the excess heat coming out of the steam generator. So that's the red arrow you can see coming out of the steam generator upwards. You can then run some additional generation, which we call secondary steam Raikkonen cycle. And in this configuration, we've got 2 sets of those because again, of the thermodynamic parameters and efficiency. So that effectively allows you to, at some point, use the extra power, so to run both your primary cycle at full output as well as run your secondary cycle and then get some extra power using the stored heat. Whereas at some other point, you might reduce the output of your primary steam cycle and store the extra heat into the heat storage. So the key components of that flexible nuclear configuration were then fed into our fairly standard energy system optimization model called WESIM. WESIM is a model we've been using for a long time. What it effectively does is it optimizes operation and investment cost for the energy system over the course of a representative year. And it takes into account a number of things, including various demand components, networks, including transmission, interconnection, and distribution networks, and it gives you the cost-optimal set of investment decisions, as well as the operation decisions for any assets that the model decides to build. So it's a fairly well-established energy system model. And then into that model, we've added, obviously, everything to do with the nuclear, flexible nuclear components, so the thermodynamic models of those components and how they behave, as well as the cost of those components are then becoming also an input into the optimization model, as well as all the other things. So the model does optimization not just for the electricity system, but also for any hydrogen demand that you also may need to meet. So it can also make investment decisions for electrolyzers or any other hydrogen production technologies. And then what it gives as an output, as I said, is the set of investment decisions, hourly operation decisions. But what's critical is here at the bottom left, that's the cost optimal size of flexible nuclear components. And by that, we primarily mean the size of thermal storage and the size of secondary or additional extra generation. And then it also tells us how much, if any, cost at the system level have been saved by making that nuclear plant more flexible. Okay, so the way we quantify the value of this flexibility is by essentially comparing two. Sorry, this has a life of its own and just keeps skipping forwards. We compare the two worlds: one in which nuclear plants are of let's say standard configuration without the other flexibility, and the other world where some of that nuclear flexibility have been added. And then we compare the total system cost and find what the benefits are as difference between the costs. We looked at a number of scenarios and case studies. There's quite a lot of detail in the papers we've published, but effectively what we try to do is see whether the system characteristics affect these choices, and that's why we took two systems that two archetypal systems that we just called North and South. The main difference between them being North is much more UK-like, so good wind resource, fairly high heating demand in winter and low cooling demand, whereas the South system is much more like, let's say, a southern European country with better PV resource, high cooling demand and lower heating demand. So we want to see if those characteristics affect the choices we make. There's also a number of scenarios we looked at in terms of what's the interest rate, what is the carbon target for the overall system, what is the cost of battery storage, because battery storage flexibility is a competing resource in a way to nuclear flexibility, and so on. So, and also just to say that in all these scenarios, we assume that in this system, which is roughly the size of the UK, we have one nuclear plant, which we then allowed the model to make it more flexible by adding thermal storage and by adding a secondary generation. And I'll show you what the model says should be done. So here we've got a set of outputs. Again, in all of these cases, the sizes of the orange bit, which is the steam generator, so that's how much heat we can produce, and the size, the light blue bits, which is the primary generation, those were kept constant. So that's, let's say, the conventional part of your plant, of the nuclear plant. So anything above that, so the dark blue thing, which is the secondary generation capacity, and the orange, light orange thing, which is the thermal energy storage, so that was optimized by the system. So for various cases, the model told us what would be the best choice of these two parameters to add to the nuclear plant. So we see that, for example, in the first three scenarios, both top both left and right, so for the north and south, the model adds roughly around, so on top of the 1.6 gigawatts of, let's say, the primary generation capacity, the model adds about 500 megawatt of extra secondary generation capacity and roughly 4.5 gigawatts hours thermal of thermal energy storage. So that's roughly translates into a duration of up to 2.5 hours. Duration means how long you would take to deplete that storage by using your extra secondary generation. So that's what the duration parameter says. So there is some variation. It's fairly robust. But what happens is that if we change, let's say, things like the battery cost or the interest rate, and interest rate obviously is something that will affect the cost of these components because everything about nuclear plants is capital intensive, then we get some different outcomes. In the north, which is more wind-dominated system, we see that the flexibility is not very attractive if the interest rate is high, whereas in the south, we still want to build some of that flexibility because in the south, we've got a highly fluctuating PV output that some flexibility will be needed for that. I'll move on because I've been warned about the time. Just very briefly, the reason why we see value from flexible nuclear is because it triggers some changes in the generation and storage capacity. So it makes the system more efficient by changing the portfolios of these generation technologies. And without going into the detail, it translates into cost savings. So this is probably the key bit, or was the key bit, where you have, let's take, for example, the first three on the left. You have a gross benefit of nuclear plants of something around 75 million pounds per year. But then again, you also have some costs because you have to invest into making nuclear more flexible, and you also have some changes in the generation portfolio. So the net benefit on the left in the first three scenarios, which are kind of your zero carbon to low carbon scenarios, are in the order of 30 million pounds per year, whereas in the south, it's about 20 million pounds per year. We can see that in some cases, the benefit drops to zero because in some cases, the flexibility is not attractive. Like, for example, if the interest rate is high or if you have not one but 5 units in the system. And we can also see that in the case of high battery costs, so that's the last column on the right, the flexibility of nuclear becomes more valuable. So that kind of makes sense because if batteries are more expensive, then having nuclear flexible is actually better. Most of the savings in cost driven by flexible nuclear come from avoiding operating costs of other technologies, in particular gas and bioenergy with carbon capture and storage, which you need to balance out the emissions in the system. But also there's a quite significant chunk of avoided investment in storage. So flexibility of nuclear in a way helps you avoid some of the investment in battery storage. Just very briefly, if you look at how this operates on an hourly basis, you can see that in the north, which is a wind-dominated system, the fluctuations in net demand, which is demand minus wind output, is what actually drives the operation of the flexible nuclear. So you can see those, if you look at just the red line, which is when the secondary cycle is triggered, you can see that's happening on the left only when the system net demand is very high, which means that the wind has gone low. Whereas on the right, which is a southern system with regular daily patterns of high PV output, you can see that you typically charge the storage in the middle of the day when you have a lot of PV, and then either side of that, you trigger some of that secondary cycle to use up the stored heat and produce extra electricity when PV is not available. So yeah, that was that in brief. So we've established that some of these benefits can be quite significant, especially because these are annual benefits, so we need to kind of capitalize them over a large number of years, and nuclear plants tend to live for a long time. We've seen that it helps if other things that are flexible are expensive. So if batteries are expensive, it's good news for flexible nuclear. But we've also seen that in different systems, we have slightly different configurations of these plants, so ideally they should adapt to whichever system you are looking at. So yes, to conclude, this has been written up in quite a lot of detail in a couple of open access papers that we published over this year and last. I invite you to read more if you're interested. And yeah, I would just like to conclude by thanking you for the attention and just saying that the last piece of news is that as of this week, I'm no longer an advanced research fellow at Imperial, but a senior lecturer at Brunel University, London. So that's very, very new, and that's why it wasn't reflected in the program. And yeah, I look forward to any questions and look forward to staying in touch with everyone. Thank you. Do you need this or?
Is this one working as well? No, it's not.
This one.
This one works, great. So I've just been told that in the interest of time, we will not be taking any questions right away, but Marco promised me he will be there in a coffee break to answer any of your questions. We'll rather move on directly to the next talk, which will be given by Andreas Olympios and Paul Sapin. Both of them, thank you, are members of the Clean Energy Processes Laboratories at the Department of Chemical Engineering here at Imperial College. And Andreas and Paul will be talking about the need questioning the need for more efficient heating technologies in future. Let me see whether I can find, you can find the talk? Great, yeah.
Just put it full screen again. Okay, hi everybody. Yeah, thank you very much for the opportunity to be presenting today. My name is Andreas Olympios. I'm a postdoctoral researcher. And together with my colleague Paul, we're going to present you some of our recent advancements in the design and integration of low carbon heating technologies as part of the IDLES program. I'll just start by stating what's the challenge of this project, and then I'll quickly summarize some current activities within IDLES that we have been doing to address the challenge, and then I'll pass to my colleague Paul, who's going to present a case study on the role of, on the potential role of ground source heat pumps. I'll just start with the main motivation. We know that there is big uncertainty in the future technology mix in the UK for heat provision. And heat technologies are not really unique in their design. They are made of different components, working fluids, and all of these can affect both the cost and performance. And there is generally a correlation between technology cost and technology performance. So one major question that arises is, should we be focusing on high performance technologies that may be a bit expensive, or should we a bit more expensive, or should we focusing on slightly lower performance technologies that are more affordable? And from this question arises another one, does the technology selection from a system perspective align with ongoing homeowner requirements? To address this, we have been looking in different kinds of models within IDLES for the last few years. 3 different projects were mainly involved in these types of modeling work. The techno-economic performance and cost models of technologies are mainly developed in the Clean Energy Process Laboratory, that is Project 2 of IDLES. But as we've heard in the morning from Jacek and Aruna, there is also a lot of ongoing work on household data analysis. That's Project 3. And then we have Project 1, where we also perform energy system comparisons of different heat technologies to identify which ones are the best from the system perspective. In terms of current activities, you've seen that we've developed lots of models of heating technologies in the last years. We've expanded them a bit. Paul is going to present some of those recent advancements in one of those. And we are also reviewing all these efforts that we have done in the last years with the main aim to compile all of this and give it as an output from IDLES. In terms of the household analysis, there is the survey that is in progress, we heard in the morning. And in terms of system-level comparisons, heating technologies are being assessed from the system perspective, as you'll see in a bit. In terms of the work on techno-economic models, we are at the moment planning to compile all of the models that we developed through the years in IDLES. Those could be heating technologies, various heating technologies, but also components of those heating technologies. We had published data that we had collected from manufacturers in the past. You'll hear more about that later in today's event. But also what we are trying to do now is also compile all the modeling efforts with the idea to have a review of all of this so that people in IDLES can easily use it, whether they are modeling the heating technologies or energy system models. And we also intend to share, as Jacek said in the morning, all household data in collaboration with Project 3 once that's available. So we are, of course, open to suggestions for any other useful outputs you think could be interesting for us to provide by the end of the project. And I'll just quickly point you to 3 works that 2 of them have already been published and 1 in the progress that are being used to tackle the questions of high and low performance technologies. I'll just jump in to quickly say a few words. This work was actually very recent. It's published maybe like a week ago. Lead author being Marco, who presented just the presentation before this, where what we tried to do was find the optimal portfolio of technologies of heating technologies for 2 systems. You heard in the previous presentation as well, a north system with cold temperatures and wind availability that is high, a south system with higher temperatures and high solar availability. What we did was to get lots of outputs from our techno-economic models of technologies, whether those are electric or hydrogen heat pumps, electric or hydrogen boilers, and we integrated them into the whole energy system of WISIM. We found the portfolios of technologies in different scenarios. And in general, of course, we see that electric heat pumps provide most of the bulk of the heat, but the proportion of other technologies in the mix depends on various system characteristics. For example, in the south, where we have cheaper electricity generation from inexpensive PV, we see a slightly increased proportion of electric boilers. So there is clearly a trade-off between high performance and low performance systems being affected by the fuel prices. Recently also, Matthias, who we saw before, published with a team a work on the impact of the energy crisis on the UK, both on the heat and power provision. They investigated the role of different fuel prices on the technology mix. And one of the main conclusions was that especially the heating sector is very sensitive to the gas prices. So the choice of going for expensive heat pumps or for cheap boilers depends significantly on the future fuel prices. And I'll just conclude by saying, by introducing this recent work where we are trying to provide optimal heat pump designs at component level, working fluid selection, compressor, all of this technology level stuff, but from a system perspective, because when we have high performance heat pumps, we may need lower electricity from the grid, but there is a trade-off between investing in high performance heat pumps or using that money to invest it in energy system flexibility or elsewhere. So there is some nice trade-offs. So I'll just pass to Paul. Before I do that, I'll just conclude to say that in general, technology adoption of different heating technologies depends on the fuel prices. When we predict technologies for low fuel prices, we see more boilers in the mix. When we see high fuel prices, we see more efficient technologies because the cost savings become more important. And those heat pumps could be air source heat pumps, which are efficient, or they could even be ground source heat pumps, even more efficient for high fuel price period. So I'll pass the ball.
Thank you, Andrea. Oh, do you hear me here, or do I need to speak in the microphone maybe? Is that better? Do you hear me fine? Okay, I'll use the microphone then. So yeah, thank you, Andrea. I quite like this slide because even though simplistic, it is very true. Like, indeed, like the lower the fuel prices, the less we need like high capex, high performance systems. While if we end up with like high electricity prices, we probably will want to invest in a more expensive, high performance system like a ground source heat pump. So that's it. I think it does answer the question very well. Let's wait for energy prices to go up, and everyone's going to switch to ground source heat pumps. So yeah, thank you very much for your attention. Do you have any question? No, of course, I mean, that's a joke, not the best one, but so no, of course, it's more complex. One complexity, at least, is that there's not one fuel. There's more than one fuel. There's gas and electricity. So if there's one thing we should look at, is really more the ratio between the electricity and gas prices, and so on and so forth. So we're going to dig a bit more to that. So I had prepared that slide to go and explain why that joke was bad, but I think it's pretty obvious. So I'm just going to switch to this one and gain a bit of time. So if we lose the whole system perspective, really, and just look at the end user, one nice indicator to kind of like compare different technologies for heating is the LCOH. So that time, LCOH is not levelized cost of hydrogen, but levelized cost of heat. So Malte has explained very well what LCOH for hydrogen is. Here, it's all the same, but you replace the kilograms of hydrogen with kilowatts of heat. So it's very simple. So basically, it's how much your heat costs along the lifetime of your system. And I've taken those numbers from IEA, not because I believe they are the most accurate, but because it's quite interesting to see that here, they tell us that, so I don't know if you can read very well, but we basically have like gas boilers on the left, then pellet boilers, then electric heat pumps, then finally the ground source heat pumps, and then some solar-driven systems. And it kind of like appears that regardless of the country we're looking at, so Canada, Denmark, France, Germany, UK, Sweden, it looks like, well, you know, ground source heat pumps are the best. They're like definitely cheaper than all the rest, really. So why do we have like only 6% of ground source heat pumps installed? So that's the question, really. So there are obviously very clear reason is that the investment cost is so high that it does represent a risk for even the end user. So this is very well captured in whole system models, but even for the end user, making the investment is one of the main barriers. The second barrier is that nowadays, that's probably what you guys think of when we talk about a ground source heat pump, is you have a big garden, you can install slinkies like here, or a borehole, you have lots of space, you live in the countryside, you've got money, it's great. Well, actually, most of households don't look like this one. Most people don't have the space to install the slinky, so there's also a technical barrier. So really, the underground heat exchanger, which not only represents typically 50 to 75% of the investment cost, is the main barrier why ground source heat pumps are not adopted more widely. So that would be kind of like the end of it. There would be bye-bye to ground source heat pumps if only we didn't have more options, cheaper options, and options to integrate those heat pumps also in the city. So there are many, many different flavors to it. For the cities, of course, there's district heating. There are many options here. I'm just listing three that I think are quite interesting. The first one is energy tunnel. So anyone who takes the Victoria line in the evening knows what I'm talking about. That would be amazing if you could recover some heat from there and directly plug it into your heat pump. Another way to basically not only integrate your ground source heat pump in the city, but also lower the investment cost for the underground heat exchanger is to share the boreholes between different households. So it's not quite district heating, but it's a flavor of it. And the last one, which I'm going to focus on today, is what they call thermoactive piles. So the idea, it's more for new builds, but it's interesting. It's basically when you build your system, in the very foundations of your building, you would basically place some water pipes and exchange heat with the ground through the foundations of your building. So that kind of would look something like that, right? So you would have like a heat pump with a thermal store in the basement, and you would recover the energy from the ground through the foundations. So some might ask whether it's foolish, because you're like, well, what about freezing the very foundations of my building? That's a bit, scary. So of course, that's something that we can't quite easily quantify and plug into a whole system. So that's why we're developing some proper comprehensive analysis of that system, where we're basically designing and quantifying everything. The second question is it viable? Like, really, that's going to cost some money, and it's going to be for large-scale buildings. So is it still like a very valid option? So for that we don't have like a very finite answer to that, but we can look today at a case study where we're looking at a 6-story office building, so typically in the center of London, and with like large heat demand and also cooling demand in the winter, which we're not yet accounting for. And so this one has like 32 thermoactive piles, so that's one building, right? And so we're going to provide the heat. So first of all, we need to design, so optimize the design and optimize the operation of our heat pump throughout the year. So I'm not going to go into too much detail, but just quickly, that's what the recipe looks like. So first, we have built a compressor database. So really, we've been taking like information from many different manufacturers for, I don't remember, more than 100 different compressors of different sizes. Most manufacturers will provide you with the performance maps in both part loads and off-design conditions. So from that, we basically have built like a big database for different compressors. And we're basically going to build for each of those compressors, we're going to build a heat pump so that we can meet the demand, or part of the demand, because obviously some compressors would be too small. And like that, we just have like a massive library of compressors with all that performance accounted for. And we're just going agnostic here. We're just saying we don't know which one's best. We're going to do the calculation for each of them. But for each of them, we basically design a heat pump by minimizing the specific cost. So we're basically sizing the evaporator, condensers, and other components to get our heat pump. And that provides us with a heat pump, part load performance, and also its cost. So that's where we'll basically then use that performance map to optimize the operation throughout the year. And I'm going to detail that a bit more. So this kind of like performance map, that's the kind of performance map we end up. So here, that's an example where I've used a 100 kilowatt compressor from Bitzer with some 2 brace plate heat exchangers for the condenser and evaporator. Again, no need to go into more detail. What is important is, what is interesting, I would say, is that in this kind of approach, we do account for the very application limits of a compressor, because you can't run your compressor at whatever speeds, regardless of the temperature. It's much more complex than that. So here we do actually have like the applications limits built in within our model. And the second good thing is that we have a comprehensive link between that design and its cost. So here we have like from the Zenodo cost library that Andreas mentioned before, we can do like a sanity check basically. So the red dot is the very system I'm talking about on the left, and we're just checking that it does correspond to most of the ground source heat pump costs. All right, so now we've got our heat pump, we've got a design, we're happy, but we need to provide the demand. So that's the demand for one specific day, one typical winter day. And we're using some varying electricity prices from Octopus Energy, so it's the Agile Octopus tariffs. And so now that's it. So we're gonna use, for example, to start with, a 200 kilowatt hour thermal battery. Okay, how do we basically supply that heat while minimizing the running costs? So that's a highly nonlinear mixed integer problem. So we're solving it with PyOmo here in Python. And that's what we get. So with our 200 kilowatt hours battery, it is massive, by the way, like a 200 liter tank, which is the classical size for an average household, is about 10 kilowatt hours. So 200 kilowatt hour, it's really for a big building. So we have a lot of capacity here, and we see that we're able to provide all the heat and charge our thermal battery while avoiding the peak electricity tariff, which obviously is not always the case. If you reduce the size of your heat battery and go from a 200 kilowatt hour one to a 50 kilowatt hour one, you see that even in the peak hours, you have to run your heat pump. So this is something you cannot avoid, and that's why doing this kind of like, developing this kind of like model where we have both like comprehensive design and operational optimization, sorry about that, we can actually capture those links and those limitations. So we've repeated that thing again so we can finally show the money. We've actually repeated that exercise for different heat pump sizes. So I was mentioning that we're looking at many different compressors. So we have lots of different heat pumps, and we use different thermal batteries. And we end up with that kind of map that tells you about the levelized cost of heat and whether or not there's an optimum. And it looks, if we look at it for that specific case, we find an optimum below 50 pounds per kilowatt hour, for pounds per megawatt hour, my bad, for like a very small heat pump and a big thermal battery. Now, this is something that is for the end user, from the end user perspective. So we know that it's okay from the end user. But now the question would be, which of those systems would the whole system decide to install really? So that's the next question. Unfortunately, I don't have the answer to that because we haven't done the exercise yet. But Matthias, we're working on basically implementing, including all those results within the whole system so that we can explore these questions and also the penetration of ground source heat pumps at a whole system scale. All right, so I had prepared some concluding remarks, but I'm looking at the time and we're a bit behind. So if you have any question, please go ahead. Thank you.
Right. Thank you very much, both of you. We are actually quite good in time now. So if there are any questions right now for the speakers, please do let me know. Yes, please, go ahead.
Malte Jansen, University of Sussex. Nice to be able to ask some questions. I see you guys focusing on ground to water or air to water heat pumps, and I've been sort of thinking, if you do air to air heat pump, wouldn't you get a much higher COP? Or is that just the sort of culturally we're not going to do that kind of thing, or is there a reason why we're not doing this?
No, that's a very good question. So I don't know if you want to address that one. But, so basically, air-to-air typically have slightly lower COPs, but it's not like it depends on the size of the heat exchanger that you're going to decide to install. So at the end of the day, it's not doomed for, like, it's not by definition an air-to-air is going to have a lower COP. It's not that simple. But the main reason why we're most looking to something X-to-water heat pump is because we're most of the time providing both the domestic hot water and the space heating. So this is the main reason really why we're focusing on that, because that's also something I would say that has been influenced by all the work that we've done with Mitsubishi, who are like heat pump manufacturers, and they basically don't develop like water to air or air to air heat pumps anymore. Not that I know of, actually. The only application would be if it's for like space heating and space cooling, so for some like very, very specific, just purely kind of like air conditioning applications. So, yeah. So, but nothing against air-to-air heat pumps. They are perfect.
Great. Are there any further questions? I think there's one in the back here. Thank you, Catherine.
Thank you. I'm Judith Ward from Sustainability First. Just perhaps I didn't quite follow, but looking at the alternative heating options, did you actually look at just straightforward electric boilers or electric thermal storage as an option? Question one. And question two, in your model on taking account of fuel costs, did you also take account of network costs associated with the different kind of heating options?
I didn't grab the second one.
Yeah, let's go.
Okay.
So go.
I knew that would be complicated. Yeah, so for the first one, so the first question about the electric boilers, yes, we do account for them. So I mean, I did run an example here where we have. I don't know if it's exactly something that you have been looking into much, but the reason why I'm going back to that one is that basically the direct electric joule heater is just by definition a very low performance, low cost system. And I think that this part of the project was really more focused on how drastically do we need to improve the efficiency of our system. So it's not something we have spent some time on. We consider it, we plug it there, we put a COP of 1, it has a cost, that's it. That's all we've done about it, really. It is in the candidate technologies that we're considering in all the systems, but it rarely gets picked up. because of the ratio between the fuel, the gas and electricity prices. Really, that's the main reason why you don't see it. I don't know if you have something.
Yeah, no, I mean it's.
So you're looking at kind of plug and play comparisons for householders. I mean, if that's where you're trying to drive this, those sorts of options like electric boilers or whatever, electric storage actually need to be in the mix.
So if you're like referring to some, say, complicated issues like this one, and you would be like, oh, would you benefit from installing, say, a 3 kilowatt joule heaters next to your heat pump? That's typically something that is done indeed. So I'm not presenting some specific results on that, but most of the heat pump manufacturers, they're very cautious about the size of the storage, and they want to minimize that as much as possible, especially for households. So their only option to do that is basically to have like a small heat pump, a small storage, and they have a backup electric heater. So electric heaters are present, but I mean, you rarely see them on their own, and they barely get picked up by the whole system model. So in a plug-and-play way, yeah, they appear as backup heaters mostly, if that makes sense. I don't know if that answers properly your question, but.
Okay, in the interest of time, I would suggest we take any possible remaining questions offline. And we now have a 10-minute break that gives us the opportunity to re-energize over some boiling coffee in the back, hopefully boiling. And the program continues at 3:25. Thank you.
already spotted that.
Okay, fantastic. Yeah, I'd say maybe just give it a minute.
Yeah.
Coffee break and cool people down.
Yeah.
Kind of getting tight in your presentations. Skip
Yeah.
avoid questions if needed.
Yeah. What
Mind
I'll.
if we finish 5 or 10 minutes late? Don't, fairly
Yeah.
relaxed.
But I think Wolfram's got a hard stop, hasn't he?
Yeah, that's true. We just need to get through about 4 minutes in. So we can't start the session any later than his session any later than 5 o'clock.
Yeah. So.
Right. Feeling okay for the intro?
No, I think I'm okay. Thanks. What I might. Gentlemen. Right. No, we need our AV guy who's hiding. Okay, hold. Yep. Okay, ladies and gentlemen, I'm afraid the weather means. Ladies and gentlemen, I'm afraid the weather means that one of our speakers has a hard stop. So could I encourage you, please, to move gradually back to your seats? Thank you. Okay, thank you very much. I'm the other Professor Green. I'm, and indeed the other business school head of department, chairing a session this afternoon. I'm Richard Green, head of economics and public policy. I've been leading the IDLES sort of activity, what should future energy markets look like, which has had 3 strands. One looking at sort of the wholesale market for energy, which is not going to be reporting back right now, and 2, looking at consumers and at the wholesale market for ancillary services. So those will be with my colleagues Mirabel Mules, who's Associate Professor in Economics in Business School, and Goran Strabak, who's Professor of Energy Systems in Electrical and Electronic Engineering. I don't think Mirabel is about to talk about our new, apparently leaked government policy, but I will let her talk about what she is talking about instead. Thanks.
Thank you. I don't know if this mic is on. I'm on number 2, in case it helps. So hi, everyone, again. I'm not going to talk about our government's policy, but my title is still Waiting for Carbon Reductions. And if you wonder what IVs are, I'm not talking about intravenous carbon today, but about some econometrics fancy term called instrumental variables. It's joint work with Felix Brack, Shefali Khanna, and Ralph Martin. I'll summarize what I'm going to talk about because I won't have much time given my colleague Goran is speaking after me. But what I'm going to show you here is we're going to be leveraging, we've been talking earlier today about the importance of data in thinking about the new energy system, and we've been experimenting with my team on how to use smart meter data to measure better marginal emissions on the grid or of an electricity generation system at given points in time. And why is it important to measure these marginal carbon, this marginal carbon intensity of the grid is because the benefits of shifting demand or changing reducing demand at certain times of the day. These benefits in terms of carbon will depend on this marginal carbon intensity. And our preliminary results, which I'll show you today, showing that this precise measurement means that reducing emissions at certain times of the day has bigger carbon gains or leads to bigger carbon reductions than can be estimated with other simpler methods. So let me step back a bit and show you, we all know that the carbon intensity of the grid has been, in the UK, has been falling thanks to an increase in renewables and a decrease in coal. But this intermittency that comes with the renewables means that the moment of when electricity is consumed becomes an important element of how carbon heavy this electricity consumption is. And of course, you know, we want to be reaching a zero carbon electricity grid, but also at the same time electrifying the important sectors of the economy. And so we are going to need to rely both on supply side and demand side for load balancing in a minimized cost approach. So of course, you know, how do we do load balancing? Is important because why are we doing it? We are load balancing because it reduces cost, but also for carbon. But if we are going to do it on the demand side, it means that users are going to have to change either in an automated way or in a voluntary way the time of the day they consume. And in another research you might have seen as part of IDLES, we've been running trials to understand the willingness to shift the time of the day you consume. But this research I'm showing you today is more about how the system responds to a load balancing. And you know, we're not the only ones to worry about it. The industry is full of new products and new approaches to offer flexible prices and demand response mechanisms. So how do we measure the content of carbon of half an hour of electricity in the system? The state of the art, which I know some don't like equations, but sorry. Here, the state of the art is actually some work that some colleagues have been working on, and is to look at the carbon content of the grid at a certain point in time, and regress that, so it means compare it in the data to the quantity consumed, and therefore to be able to understand what are the emission factors. However, this approach becomes, don't worry about the equation, I'm going to tell you in words what the problem is. The problem is that when there are more renewables in the system, it is less likely that what you are consuming, the electricity you're consuming, is independent of its carbon content, and at the same time, and because weather, the weather that's whether the wind is blowing or the sun is shining, is not only going to influence the supply of electricity, but also the demand of electricity. You're going to heat differently, you're going to air condition or be outside or go to the park differently if the weather is different. And from a data point of view, this is an important consideration because you are affecting at the same time the demand and the supply of electricity, and therefore both can't be considered as independent. In addition, because of the increase in renewables and the price and market mechanisms that are out there in terms of demand-side response, again, your demand isn't going to be independent. So what we do is that we take a new econometric approach where we are going to use a large sample of households' smart metered data and detailed weather controls to come up with a finer measure of what the content of carbon is, what the carbon intensity in the grid is. So we use national grids emissions data and then weather data and smart meter data for 1,100 Octopus customers across the UK. And the important detail about that data is that we know that those customers are not on flexible tariffs. So it means that their demand is not affected by the price at a certain time of the day, which is therefore not affected by the weather. So I'll skip the detailed specification, but what's interesting is with this estimation, what does it tell us? So if you just take, the most naive way to compute the average carbon intensity is to take the average and not the marginal. And what you see here is that through time, the number of half hours in a year that would yield. Okay, this is the, sorry, step back. Let's take an experiment. I'm going to shift 1 megawatt of consumption in a 30-minute period to another half hour at some point in the next 3 hours. It's an exercise. We could do something else, but we had to choose something. So let's say I move these 30 minutes of consumption now to 5 p.m. today. What is the carbon reduction I can achieve by consuming at 5 p.m. rather than now? Okay, so measuring this carbon reduction, either I just take the average half-hourly consumption of today or half-hourly carbon content of 4 p.m. in September, but our finer measure means that in 2020, there were 25% of the half hours of the year could lead to, by moving my megawatt from that half hour to a next one, would reduce the carbon intensity of my electricity consumption by 20%. And whereas in the naive case, I was only reaching 10%. And if I then include the weather controls and the usage of my smart meter data to estimate that better, the reduction is not 20%, but in 25% of the half hours, I can actually reduce the carbon content by moving that half hour to a 50% carbon reduction. So to conclude, and I'm gifting a bit of time to Goran, the UK power generation grid has been dramatically cleaned up, but this shift not only affects the average carbon content, but also the marginal emissions that come with electricity consumption. And if we want to optimize the use of demand shifting and from the demand side, we can use finer data techniques to improve the value of demand shifting. And that is very important when we're thinking about investment and around the system, but also in designing the market, because the return from demand responsiveness can be estimated better. And what our initial findings are is that there's a higher value in demand shifting than what can be estimated otherwise. So thank you.
Thanks very much for giving me a minute. Yeah, can you hear me, colleagues? Is that okay? Yeah. As mentioned in the previous presentations, there are massive challenges associated with decarbonisation of the electricity system, particularly related to this increase of contribution and penetration of renewables. And already colleagues have mentioned, and also Caroline, about the frequency stability, which is increasing given the reduction in system inertia. So if you lose a big generator, it's going to be a big challenge to make sure we don't have a blackout. But how should the market evolve is something which this modeling is being focused upon, and also how relevant, but also how what the implications would be in here. That's what we're going to focus upon. Maybe I should just mention that if anybody finds any errors in here, it's not my fault. It's Carlos Matarella and Yi Wang and Davei. This is just to illustrate the implications of, you can see on the left-hand side, is to do with the overall cost of running the power system. And we have in here, there is both ancillary services, which is maintaining the stability of the system, how much it costs to make that happen. And you can see that, what you said yesterday here, historically, that this was only 1.5% of the overall cost. So that wasn't, so there was no really a market for that properly done. But now going 2030 renewables, you can see that reduction of energy costs, would nearly half, while the ancillary services costs are going to increase potentially more than 10 times. And the question is how we're going to move this forward, and should we, how this should develop given this massive change. This is also showing that what's called this value frequency response, which is the ability to maintain the frequency when we lose a big generator. I'll show that in a minute. That's showing, you can see that this is increasing, kind of more than 10 times between 2030. So historically it's going to be very massive, and that's why we are in here is how the market should evolve to put this on the agenda. A bit again technical, but I'll try to be simpler than here. One of the core aspects of the modeling which is being developed within IDLES is the big challenge is to model the energy system, which is kind of minutes and hours, versus together with frequency stability, which needs to be looked at into, fractional, of a second and second time scale. So how you link these differential equations which respects flexibility, frequency with energy, this needs to be, and this is something which is being developed, and this is a very significant contribution of this work. You can see at the bottom is the kind of, which is the frequency in hertz. You can see 50 hertz, that's what the frequency is. It changes a little bit, but then if we've got, you can see in here, if you've got a loss of generator, then it falls down very fast. And this is where we need to meet the constraints of what's called ROC-off, which is rate of change of frequency. How much frequency we would allow to change in terms of fast. Should it be slow or fast? And given how this is going, much faster reduction, which is also a very big issue. And also the frequency shouldn't go below 49.2, which is nadir constraints, to make sure that, again, we maintain stability. Because if we go below that, there may be outages of other generators and so forth. So these are the two core constraints which need to be taken into account and manage them. And also we want to kind of, within say 10, 15 minutes, to go back to frequency being, we increase the power, so we get back to 50 hertz. But the core aspects in terms of the constraints are this ROC-off, rate of change of frequency, and also what's the minimum level which we need to maintain. Just to show you regarding this inertia value is changing massively. So you can see at in your side, on the left-hand side, we've got what is the value of this system inertia, which is rotating mass, because it's critically important for maintaining frequency regulation. So you can see if demand is very high, in here 60 megawatts, and wind is not blowing, we don't care, value is 0. It's not relevant. But if demand is lower and wind is blowing hard, you can see this is increasing massively. And that is where the core challenge is, to make sure that we can actually maintain the frequency properly. And that's all to do with this, wind is making, because there is no inertia from renewables currently. And also what we have done also, this was part of one of the white papers, we showed, for example, that in COVID, when COVID started, May, July, you can see that there was 3 times increase in frequency regulation costs, 300 million. And it was to do with the fact it was that demand reduced because people were not going to work. And also it just happened to be a bit more windy, and that created massive increase in frequency stability. So the inertial related costs were very big. This is another case, just to show you again, regarding these links between energy production and frequency regulation. This is just showing there is this what's called enhanced frequency response, which is kind of how we can do this fast rather than historically, which is slow. In here, we now, for example, batteries can inject power fast when you lose a generator within a fraction of a second, and that can maintain the stability. And you can see in here that this is just to show, if the EFR is 150 pounds per megawatt hour, and what the net demand is changing given the wind is blowing and so forth. So you can see that when net demand in gigawatts is low, then you can see that we are buying 700 megawatts of enhanced frequency response. But when demand is high, which means that wind is not blowing, you can see that we don't want to pay anything. And that's also very important to make sure that we've got a proper market working on this. Also, this is just showing in here how the links between primary frequency response, which is what generators have been doing, conventional generators have been doing in the past. Historically, they are part loaded, and if you lose a big generator, they can increase the power to maintain the balance. But you can see in here, depending on kind of what the net demand value is, this is just to show that we will potentially pay, if net demand is 20 gigawatts, we are going to pay potentially 7 times more than what we will pay for primary response. That is, but if demand is high, 60, then we will do just a little bit. Also, there is a massive importance of linking, as discussed already, energy, but in linking also the frequency response with the inertia. And this is just showing, this one is showing that that enhanced frequency response, which is this battery, which can increase the power massively fast, so we can deal with, we can live with a much lower inertia in that case. And it's just showing in here, you know, how much of links between enhanced frequency response and the inertia. So you can see in here, if we don't have any enhanced frequency response, you can see in here we need 300 gigawatt-seconds inertia. But if we've got quite a lot of enhanced frequency response, then we can live with 6 times less. So putting this together is critically important. Oh, sorry, I need to, well, let's then drop this one and just show this. This is just showing also that this work is also informing potential development of new standards, because, you know, at present, the frequency response cannot be higher than, rate of change cannot be higher than 0.25 hertz per second. But the question is, you can see that this is just showing what the costs are per year. You can see we are talking, you know, getting to 3 billion by 2030. But if we relax that, and we say, okay, it can be even 0.5, we can deal with that, then you can see that the frequency response, that the cost would halve. And that's also, there is a big discussion about the changing of the standards. This one on the right-hand side, as mentioned, you know, currently wind is not providing inertia, although there is a rotating mass. That's to do with the control and so forth. This is just showing that if we start having a synthetic inertia from wind, that would reduce the cost of auxiliary services 5 times. And that's also where the market is required to make sure that there is enough revenues for that in place. So we have developed this model, which you also see in some of the details. And they're just showing the how the frequency changes when we lose a big generator, which is large nuclear or small nuclear, or we use in here offshore wind, which is also very relevant because there will be kind of, you know, big cables in there. And you can see in here that there is also in here rock off, which is this straight line down. So the frequency must go this way, not the other way, showing how relevant that is. And that there is also importance in here that we make sure that the providers of these services can access the revenues. This is just a quick example to show the market which is being developed. On the left-hand side is the profiles of demand and supply. You can see in here that I can show this. No. Okay. There is in here in the middle is the wind blowing, and you can see that wind is dropping around, you know, you can see around hour 80 and 120 goes to small numbers, and that means that you can see in here that the frequency response prices are then, you know, sorry, the inertia prices are 80 and 120 are low because, you know, there is no wind, we don't have a problem. Energy price is obviously high because we're now burning gas and so forth, while also the frequency response prices in 80 and 120 are high because we've got important requirements to maintain stability. And this is just to illustrate. We have now changed this and showed that the auxiliary services market should be paid by generators because they are core reason for having these results, but also this is, you can see in here per unit and balance per technology. The negative is the costs, and we have allocated here the largest plant pays the largest amount because but all the plants pay something. So this is the negative in here. There are 3 different ways of calculating this, and on top of that is what the money is generated, because there is also, for example, nuclear has got inertia when it's rotating. Well, you can see offshore wind is, regarding zero, is only paying for it because there is no inertia. But that will be also, again, challenge for them to potentially do that. So you can see on the, you can see that, there will be potentially, 50 million per year for offshore wind to pay because of these requirements for frequency regulation services. And also nuclear, we also pay because they're also large. While other generators would get paid because they provide inertia and they provide also, primary frequency response and enhanced frequency response. Yeah, sorry, yeah, and then this is a quick summary that now we have developed a marketplace which can now allocate properly the costs of auxiliary services and also pay appropriately providers of these services. And so the inertia and frequency response services, get paid. And also there is now, obviously, in here, there is also now other issues which we are working on. Also how the flexibility resources can be included, such as demand-side flexibility. Also we want to include also interconnectors in there, but also demand losses. Currently in here is only generation losses, but you can also potentially have a big demand loss, which would then increase the frequency, which also needs to be managed, because it would also lead to instability. So that is, and we also need to move forward more when we go to nearly zero carbon system, when there is no kind of gas plant and so on, and how that would work, and how the stability would be critical. And that's where the potentially massive benefits of ability of renewable generation to participate in this will be very important. Thank you. Sorry for...
We've got a moment or two for questions. As I say, I'm conscious of speakers with hard stops. But I don't know if you want to go near the stand so you can use the mic. Goran should have got a separate mic. Do we have any questions for either of them? And remember to say who you are. It's the green mic number.
Hello? Is that well, Capella, hi. Yeah, Thomas Powell. No, thanks for both the really interesting presentations. So my question's for Goran. At the beginning of your presentation, you showed that you saw forecasted cost increasing for frequency services quite significantly. I was just wondering, today we're seeing, in the DC market or dynamic containment market, we're seeing saturation. We've got a big pipeline of battery units coming online as well. So I was wondering, does that forecast take those parameters into account? Thank you.
Yeah, it's a very important question. This was done, this was the extreme case without dynamic containment and without kind of batteries. You would just say how this would be if we continue only with generators providing frequency response. You're absolutely right. I mean, there is a significant now, because there are also payments for this, but still the market is not properly in place.
Okay. Any other?
The payment in particular, who should pay for that?
Okay, if not, and conscious of the timing, thank you both very, very much indeed. So it's one of the benefits of an interdisciplinary project like this is if you've got a very good memory for detail, and you were here last year, Ian Staffel presented some joint work, actually with me, that used a Shapley value as a way of allocating carbon reductions, and Goran has remembered that Shapley value and his team have used the same concept as one of the things inside this work. So we now have a quick fire presentations of three of the things that we've done. Firstly, Wolfram comes back to actually be a speaker on the use of machine learning methods to inform policy making and energy models, followed by, and he gets 5 minutes, NB, then 10 minutes each from Matthias Mersch and Phil Clemmo. Matthias is a research assistant and PhD student in the Department of Chemical Engineering and the Centre for Environmental Policy. I'm not sure if that's one role per place or what. He'll be speaking on the team's technology database of energy technologies. Phil is a senior teaching fellow in the Department of Electrical and Electronic Engineering, and he'll talk about the role of the Hitachi-funded digital energy demonstrator in the IDLES program and the future plans for the demonstrator. So, Wolfram.
Thanks a lot, Richard. Sorry, we have to ask for your patience for a moment. We have two screens here, and one is being displayed. Unfortunately, that's the wrong one. That should do the trick, thank you. Okay. All right, thank you. So my name is Wolfram Wiesmann. I'm at a business school here, and I would like to give a brief update of a project on trying to understand how uncertainty affects energy models of the future. And this is a joint work between two projects of the IDLES program that is also underlying this conference here. It's a collaboration between Work Package 5 that is led by Goran Strbak and myself, as well as Work Package 6 that is prominently led by Ian Steffel, as well as some collaborators from ETH Zurich. So, as we all know, of course, the future, and the one thing that we probably understand about a future energy system is that it needs to be designed under significant uncertainty. And to my understanding, uncertainty in the design of energy systems is typically accounted for by looking at energy transition scenarios, so alternative views of how the future may look like. And I've been informed by my energy colleagues that typically these energy scenarios are generated in one of two relatively extreme ways. One way which we could characterize as the quantitative way, and another one as the qualitative way. In the following sense, many people use optimization models to design an energy system of the future that is optimal in some sense. And since we don't know how the future will look like, what these people often do is they don't just generate one optimal future energy system, but many of them. Two prominent techniques here are modeling to generate alternatives. What this technique does is it doesn't just create one optimal energy system, but it creates a lot of almost optimal systems that are as different as possible so that we begin to understand the potential trade-offs that we may face. Another approach are the so-called uncertainty-aware models, where we explicitly vary some of the key parameters, or parameters that we believe to be key, and try to understand how the optimal energy system configuration changes in response. Those approaches are great in terms of their mathematical rigor. We can characterize their features. We can hopefully say something about their optimality under certain assumptions. The problem is that many of those studies generate a large number of scenarios. We have looked at two case studies that I briefly touch upon later on that have, I think one case study has 441 scenarios and another one has 1,000 scenarios. So 1,000 different energy system configurations, and we should try to understand what those 1,000 scenarios are telling us. On the other extreme is the qualitative approach, which involves stakeholders to try to understand, to generate a small number of storylines of how the future energy system could look like. The great thing here is that we end up maybe with 2, 3, 4, or maximally 5 different scenarios. That can be explained well to policymakers, and the trade-offs can be understood. The problem is here that, at least in the initial stages, this is often based on subjective judgment, and so they may be open to more bias than perhaps a mathematical model. So what we try to do is to find some way in between those two extremes. And what we did is we did start with a quantitative model, but what we try to do is we try to leverage machine learning techniques to take this large scenario space and reduce it to a few storylines that hopefully explain the main variabilities that we face in the future energy system. In a nutshell, our approach is based on the following process chart. We first define what outputs we're actually interested in an energy model. Typical energy models might involve thousands or tens of thousands of decisions. We don't want to look at all of them, but we want to look at some of the key decisions that may differentiate different energy configurations for us. We then use a clustering approach, k-means clustering, to find configurations that are quite similar to each other in terms of these outputs. And then we use classification trees to come to an interpretable summary of what we have clustered. And we have applied this to 2 case studies. The first one is a global decarbonization case study, which looks at how our energy system worldwide might look like in about 75 years. This case study was generated 1,000 scenarios, and we use clustering and classification trees to decompose those 1,000 scenarios into a small tree that shows us the major decisions that differentiate those scenarios. So in this particular case here, sorry, I forgot my glasses in my office. In this particular case here, it turns out that those 1,000 scenarios, one main differentiator between them is whether or not we will be able to electrify heating. And that is the first branch of the tree. And then depending on if we achieve the electrification of heating, there are then 2 further scenarios which are based on one other key decision. And then we have these radar plots which show us for different criteria, which probably neither you nor I can read, what kind of flexibility we face in those remaining scenarios that are subsumed under this part of the tree. Here's the second case study. It's a European case study that looks at potential future energy systems in the next 25 years in Europe. And again, we start out with 441 different system configurations, which would be very difficult for a policymaker to look at in detail and understand how they differ. And using our technique, we can again come to a fairly small decision tree that summarizes the information that is captured in those scenarios. I think my time is up. Thank you very much for your attention, and I'll move on to Richard, who might announce the next speaker. Thank you. Thank you very much.
To leave, so have you got 30 seconds for if there was a clarification?
Absolutely, of course. I have to say I'm more responsible for the machine learning part than the energy part.
Oh, the other one, sorry.
It seems you were clear enough anyway. So, and it should be Matthias. So, and you may even have some slides in a moment.
I do have some slides somewhere.
So.
That'll do.
Okay.
Yep, that works. Okay, thanks very much. I don't want to take too much of your time because I'm very aware that I'm between you and the drinks and canapes afterwards, so I'll make it quick. But I've been asked to highlight some of the key outputs that we've generated from IDLES, and this is specifically IDLES Project 2. So again, big credit, you're probably getting tired of this, but big credit goes to Andreas and Paul and Marco and Christos, who really did the bulk of the work, and I'm just standing here and presenting it. But basically what we did, so the aim of Project 2 was to really characterize technologies that will help us to reach net zero. And this is from a cost perspective and also from a performance perspective. And what we've done here is to generate a library for a whole bunch of different technologies, and this is just compiled from open literature, from manufacturers, from academic papers, where we look at, costs and performance of various different domestic and commercial technologies that are useful in low-carbon energy systems. So I've put the big QR code up there if you're interested, or if you get the slides, you can click on the link. So what the library contains is cost and performance data for the different technologies, and the important thing here is that this is all commercial data. So we've gone to manufacturers, we've looked at data sheets, we've looked at product brochures, we've looked at just online marketplaces, and we looked at, okay, how much do you actually have to pay to get, one of these units, for example. And then we've also looked at data sheets to see what's the claimed performance of these technologies. And the idea was to get as much data as you can to get sort of a representative figure of the whole market, and to not be biased, because normally if you do energy system modeling, you pick the first value and you're not sure if it's high, if it's low, if it's representative, so we try to compile as much as possible. And we are specifically looking here at various different heating technologies, so all sorts of different heat pumps. Well, not all sorts, because again, I don't think we have air-to-air in there, I'm sorry. But we've got air-to-water and ground-to-water heat source at domestic and large scales. We've got different flavors of boilers, so your classic gas boilers, your counterfactual, but then also electric boilers, hydrogen boilers. We look at hot water storage systems, we look at CHPs, different flavors. And then also solar systems, so PV panels and also solar thermal collectors and PV and thermal collectors. And then we have not only whole systems, but also some components. So Andreas also already mentioned compressors that we looked at in quite a lot of detail, and heat exchangers. And these component costs also help us to optimize the system design. And then in terms of performance, so we've got the nominal performance for all these different things, but then specifically for heat pumps, we also looked at quite a lot at off-design performance. So performance at different temperature levels, so that's source and sink temperature, and then also different, well, if you only run it at part load, for example, and not at nominal load. This is what it looks like. It's a big Excel sheet. You don't need to, I'm not expecting anybody to read this at the moment. But basically, we try to get all the key figures that you need for your energy system modeling for all of these technologies. So in this case, for the heat pump, it's the COP at different temperature combinations. It's the cost. It's what sort of unit you have, what refrigerant you have in there, and then also importantly, the year for which the data was collected, because obviously the costs might change over time. And this allows us, for example, to look at things like economies of scale. So here it's just plotted for the air source heat pumps. How do the specific costs, so pound per kilowatt, change with the size of the system? And you can see the spread of all the different data points in the market, and you can sort of draw your line through them. And this is an approximation of the economies of scale that you can expect, which it's even more visible if you look at the ground source heat pumps on the right-hand side, where you really see how larger systems drive down the costs, because you just get more output, and for the same initial investment, only a slightly higher initial investment. Same for, so this is just the energy storage, similar trends. And you can also see, as I mentioned, the spread in the market rather than just looking at single values. And same for the kind of, so this is what I alluded to, for the heat pumps, the off-design performance, or the performance at different temperatures. And this goes back to what Andreas presented before, that you can look at high-cost, high-performance systems versus low-cost, low-performance systems. So all this data is available in the library. We've written a short little user guide. And we've seen quite a bit of attention, which is obviously nice, and it tells us, there's demand for open data and interest in these technologies. I'm sure the 1,100 other people who downloaded it are also writing some nice publications at the moment. But yeah, and we've also been able to feed the data into other IDLES work, which is quite nice. So I'll leave you with the QR code, and I'll be available for any questions. Thank you.
We'll gather questions at the end, and so Phil, if you can come up, and then stay near.
Hi, so my name's Phil Clemo. Presentation's titled about the digital energy demonstrator, but that's really the room where I work rather than what I work on. So what we're going to talk about as the IDLES output is, I suppose, a model data set that we've called Gridlington. Thank you, Catherine, for the name. Essentially, we were tasked, a small group of us were tasked with trying to present and demonstrate outputs of IDLES, because it's all well and good, lovely papers, all that sort of academic impact, but it's very hard for that information to be parsed quite often by members of the public, non-experts, sort of a wider audience. And so the aim was to have demonstrations within the demonstrator that are sort of a bit more, approachable and parsable. And we wanted a setting for that. Initially, we were we remained focused on realism. So initially, we sort of targeted actual real-world data, members of the IDLES group that are able to present that. But we found it very difficult to work with, acquire data that's compatible, workable with each other, complete, consistent, from any one source. So Gridlington was then built from the ground up, which has presented itself with a number of sort of useful features in the end that were probably better than going with real-world data. So we've taken the input from a number of different IDLES groups. So largely for the fairly small group we started with, there's a lot of work from Goran's group, Marco and a few others, a lot of work with Jacek and Iruna, and within electrical engineering, people like UA and Tim and people like that we got the electrical modeling. So what have I put in Gridlington, I suppose, is the first question we should ask. So from the sort of future grid planning group, from Marco mostly, we've taken an energy mix. So the pie chart in the corner, this was not designed for such a large screen, but the pie chart in the corner is almost readable. It's showing us the energy mix we're working with. So we've got a grid that's fed, in this case, the blue ones are wind, the purple one is storage, orange is solar, and the rest are probably not worth worrying about. So we're largely a wind, offshore and onshore, and storage-based grid. This is a grid of the future. That feeds into an electrical system model. So the electrical system model is partly transmission level, so that's come from National Grid ESO, data that's provided that's realistic for the real grid. Into that, we wanted to look at a sort of more local scale, so that we wanted to look at town scale rather than national scale for this, because we wanted to start looking at what the end users are going to be able to do. So within our national grid, we have embedded a much smaller town, and this is where the name Gridlington comes from. We took a real town, took the geography and the buildings from that real town, and applied a generated electricity network. So it's the electricity network that would exist for that town, rather than exact data for that, for the town of Sandy, as it happens in Bedfordshire, a small town. So we've got an electricity grid with supply, with wires, with nodes, with connectivity. We know how everything's wired up and all of that. Into that network, we need to apply a demand. Otherwise, it won't work as a simulation of the real world. And sticking with a sort of realism theme, we didn't want to just apply numbers to each house is X kilowatts or a basic profile. In order to enable a lot more flexibility and sort of realistic views of what's going on in that network, we wanted the network demand to be realistic and represent what real people do. So that was back to Jacek, who I don't know if he's in the room, but he developed an agent model that provided us essentially our agents are representing each household, and they have a thing that they are doing at any given time, whether that's working, cleaning, cooking, just staying, relaxing in their home. That then translates directly to an amount of load and a place within that network. So our agents have a home and a work. If they're at work, their load is at work. If they're at home, their load is at home. So that's represented down in the bottom of this set. So this shows that this represents one agent household under a number of different conditions, whether that's different weathers, different days, is it a weekday, weekend, that sort of set of things. I don't know the exact scenarios that Jacek's graphed for me, but it shows that at a given time, our agents aren't doing all the same thing, and that allows us to work with them a bit more intelligently. So a few stats on that. This image shows just the HV network, so the 11 kilovolt network within our system. hanging off each of those nodes are all of our houses. I didn't want to put up a map because it would be bewildering, but we have roughly 10,000 nodes in the total network, so it's a very high detailed network. Comparing that to our national network, which has got about 36. So we've focused all of our effort and detail on the small town. Most of those are in the 400-volt network, so we've modeled all the way to every single house. We don't always run those in every simulation, but we have the data available to us. And then we've taken all of that data set and we simulate it within a real-time system. The real-time system allows us to interact with it in a human timescale. Rather than clicking go and the simulation either comes back in seconds, and that represents hours of data, or often with these simulations it comes back in hours and it represents seconds of data. The real-time data means that a second represents a second. So if we want to do a 6-hour simulation, we can speed it up a bit, but it takes a long time. I think our fastest speed up is 6 hours and 6 minutes. But it allows us to switch switches, command the agents to do things like that if we want to. Not developed yet, but will allow us to do it. So with all of those data simulating for demonstrations, the first thing we've taken to do is a fairly simple sort of first scenario, which is mispredicted wind. So we've taken a misprediction of wind. The wind power has come, I think it's in the region of 2 hours later than they expected it to. So there's a shortfall for 2 hours, and then there's an excess a bit later on. And really what we wanted to show with this demonstration is that the network, the model behaves realistically. It's not necessarily that this is a magical new result that no one would have expected to happen. The proof is really proving the model rather than the result. So what we've got from our population, this is a snapshot towards the end of that time. So all of the activities are static, but this just shows that each household does have an activity, and each household with an EV, the EV is doing one of 3 things. It's charging, traveling, or idling, depending on what color it is. So we model all of that, and we've requested that our agents use less energy during this period of time, and they can recover it later, recovering it slightly slower than they took it in the first place. And again, as I say, it's a fairly potentially trivial result. Our population essentially reduced their usage because they were asked to. They did it, as you can see on the top right one here, they did it largely through not charging their EVs during that period of time. They want to recover their situation, but obviously we don't want to completely disturb the network once everything goes back to normal, so they recover it much more slowly, and you can see that on the right-hand side of that graph, they recover it slowly. So as I said, the result is not the thing I'm presenting here, it's more the model in the data set that allowed us to create the result, and moving forwards will allow us to create more results. So Gridlington is definitely not something that ends with IDLES. The aim at the moment is to integrate either more scenarios within the sets that we've got, so more things we can do than just a basic wind misprediction within our existing data set, or rolling in more parts of IDLES or more collaborative work. So a good example would be adding in heat demand within these houses and allow that to be presented on the grid or not on the grid. And then Gridlington, because it is so flexible and we've got all of the data for it, it's not like we're scrabbling for data from here, there, and everywhere, that allows us to take a data set we've created for IDLES and use it in other places. So the first place we're likely to end up using it is within the EEE electrical engineering teaching. It allows us to take a realistic setting and embed examples within it. And those examples can be either found within the network, we find structures that create the behaviors we want to teach, or probably more likely, we slightly alter parts of Gridlington and allow it to demonstrate the behaviors we want to teach. So things like, well, what happens if a whole street gets solar or a whole street picks up EVs? We can show in simulations to our students, this is the result. And then within a student environment, much more likely to be able to do things like, well, how about we do this? Well, take answers from the students. Do you want this percentage, that percentage, things like that. That really is where we lie with Gridlington. It's much more a data set and not without wanting to sound too preachy, an idea than it is a given demonstration that I will do in this room within the electrical engineering department. So that was all I wanted to say about it. I put a little thing on the end there. If you want to come up here with me,
Okay, if we have any questions, they are not keeping us from the drinks. We are giving Tim more time to think about his concluding results.
Tim's keeping us from the drinks.
So again, I'm on the green mic.
Hello there, Nick James again. Just a quick question about your Grillington experiment. I'm living in the town. I have an EV. I need to go and see the doctor. He's in the next town. I need to take my car out, and I've got to charge it so I can get to the appointment. And it's at the peak time. What are we going to do? Are we going to be using non-nuclear base load to cover that peak period, or am I just not going to be able to make that doctor's appointment, assuming there's no bus service?
So, to an extent, that's the kind of question we developed Gridlington to be able to answer. So to answer that, slightly avoiding the answer in my own answer, we would, if you wanted those kinds of answers, we would set up scenarios within Gridlington, run them, and show you the alternatives of what would happen. The network that was provided to me by Marco is essentially a viable electricity network. You shouldn't end up in a situation where you're going to have not enough power to do what you need. So it's unlikely to be presenting you any big findings in that level, the sort of national generational network. The kind of findings you might get from Gridlington that is well suited to are things like, well, how would the incentive structure to help you decide whether to charge now or have charged hours in the earlier, or keep a certain amount of energy in your EV battery in case of this doctor's appointment, building the structure to finance that and how that's communicated to the end users is the kind of thing we would want to build within Gridlington, rather than, you know, is this energy coming from nuclear? So I think
some of the economists within IDLES are thinking about work showing how much you'd save if you were to do the charging in advance of time, which is not always possible. So in an emergency, you just, I'm afraid, have to pay a bit more. But hopefully there would be enough other people who would find it possible to charge at a time that helped keep everybody's bills down.
Can I have the question for the cost data sheet? And so I think you might get most of the data from the suppliers, and the installation cost and the final project cost, it might vary very much.
Yep. That's a very, very valid point, I think. So yes, we've gone to the manufacturers, we've looked at the manufacturers, how much they're selling their technology for. And then where we've done, and I can only talk about our modeling, is we've gone into, so BASE, New Desnes published quite a few reports on, what does it cost to install heating technologies in different homes, depending on, what you had in there before, how much, how many measures you need to take. But yeah, you're correct. That's not covered in the data sheets that we published.
Yeah. So can I just give 2 examples? I hosted 2 PhD students test their cost model at Equinor, and they put all the components and like one offshore wind farm project, something like a few hundred data put. So we had a blind test. So then come out is something the total cost is only 10% of the real cost. And also our own cost model at Equinor, we are in principle, we had a very rich operational experience and many project experience. I have worked for 28 projects, and our Equinor's own, this cost model, it's very dependent on so many facts. I had 28 projects, and then I had 5 projects, and we utilize Equinor's own cost model and all the costs from all the suppliers. We have 5 projects, our cost is doubled. And so the project during different phases, and this cost will become more and more accurate. So it's a big difference.
Yep.
And
point taken, but I think it's also important to consider that, these large industrial commercial projects that you're talking about are probably something very different than, somebody going out and installing a heat pump or installing a hot water tank or installing a boiler at their home. Because obviously these projects, as you mentioned, they're exposed to so many different things, different financial markets, different, suppliers and supply chain issues and labor and all of that. And it's a totally different scale compared to going into a building, putting a new technology into the building where, you pay some installer to come to your house for like a day or two and they do the work. And yes, it's a significant fraction of the cost, but I don't think it's as unpredictable as, the cost of these large-scale projects that you are referring to.
Okay. Well, thank you all very much. Wolfram, I believe, is willing to answer questions by email. It's a very simple email address, which is www, 2 letters, not 4, at imperial.ac.uk. And now I will thank you again to Matthias and Phil, and I will hand you back to the original Professor Green.
I'm not sure about original Professor Green. I chose other Professor Green for my Twitter handle because there was a much more famous Professor Green already on Twitter. But already Twitter seems like history, doesn't it, somehow? I'm not going to detain you for very long at all, just a couple of quick remarks. So first of all, we have arranged some drinks and canapes just to give you another chance to just chat with presenters and to network with friends and colleagues in the audience. So that's in what we call the senior common room. So you leave this room and this building on this level, walk back along the walkway, part way towards Exhibition Road, and there's a room on your right called the senior common room, and we have a reception in there. There are enough Imperial people in the audience to be able to find someone and follow them, and they'll know where that room is if you're not familiar with the campus. I would like to thank a number of people. It's the classic way to close a conference, isn't it? But genuinely, thank you all for attending and for asking questions and debating. That's what makes these events so interesting. Thanks to all the speakers, to the 3 people who joined me as a panel for the briefing paper launch, and for Carolina for giving a keynote address. I thought all of that really worked very well. I was pleased with it. If you have items of feedback, then we will be providing with a mechanism to do that. There are some other people to thank as well. Behind the scenes, there's a steering committee of some academics from other universities and some people from third sector and public sector, so from GLA and from Old Oak and Park Royal Development Corporation and so forth, and Bays, who've given us a lot of advice and insights along the way and helped us frame the project. It was a 5-year project, and we took points along that journey to recast and reshape our questions, and the steering committee were invaluable in doing that, and I thank them a great deal for doing that. And I also thank the partners, so EPSIC for being the people who funded and got us going on this project, but also all the people behind the logos that I splashed at the beginning of the day. So the large industrial concerns and some of the SMEs and other companies who, again, have been tireless, really, in attending meetings and giving us advice and insights and engaging with our researchers. It wouldn't have been the same without those. This being the 5th year of a 5-year project, this is the last time we'll gather in an event this size. But we still have 3 briefing papers to launch, and so we will have launch events for those. They will be an online attendance and an in-person attendance option. They will be hybrid events. So we will make sure you're aware of those by the normal sort of email circulation. And with that, I invite you to join us for drinks, and thank you very much for your attendance. Thank you.